to the organizers. Can you hear me? Yeah. For including the paper in the program. I'm going to present Simulating the Survey of Professional Forecasters. This joint work with Anne Hansen, John Orton, Sofia Kazzini, and Alisa Rifornarvar. Anne and Sofia are here in the audience. And Anne works for the Federal Reserve Bank of Richmond, so the usual disclaimer applies. So I would like to start with a quote by Jeffrey Hinton, the godfather of AI, stating, "I now predict 5 to 20 years, but without much confidence. We live in very uncertain times. It's possible that I'm totally wrong about digital intelligence overtaking us. Nobody really knows, which is why we should worry now." So I decided to include this quote for a couple of reasons. One is kind of ironic. We are in a conference on forecasting, so here is an expert making an admittedly uncertain forecast about the impact of AI. The second is, jokes aside, is more serious, is we're not in this paper concerned about AI overtaking humans, but indeed economists still face a lot of uncertainty about the use of AI as a research tool. And indeed, while LLMs are increasingly used as forecasting tools and synthetic agents, we still know relatively little about which aspects of human expectations and behavior they capture well, where they systematically differ from humans, and for which applications they're most useful. So here, in this paper, we use large language models to study expectations, to explore AI as a research tool for studying expectations. So why surveys and expectations? Expectations matters, but are not observable. Economists and policymakers rely on surveys as one of the measurement tools, right, for capturing expectations about future economic indicators and conditions. Surveys, as any other method, offer benefits, but also they face limitations. Among the limitations, they can be expensive, low frequency, rely on small sample sizes, and lack flexibility, for example, in terms of the instrument, adding questions to the instrument or changing the wording of the questions, and so on and so forth. So in terms of low frequency, there are other approaches that have been used also to increase the frequency of answers, econometric approaches. Giesers and Wright have a paper. Here we use a different approach. Again, a large language model, and we ask whether they can provide a scalable and accessible approach for simulating expectations. Of course, we're not going to provide the final answer. There are many papers studying this type of questions, but I'll tell you what we find. So in terms of what we do, we simulate the survey of professional forecasters using a large language model. We create personas based on a set of hand-collected panelist characteristics. We provide the model with personas and data. I'll tell you which pieces of the data we provide to simulate AI forecasters. And we ask a forecaster to provide forecast for many variables at different horizon lengths, similarly to the professional forecasters in the survey, in the Philadelphia Fed survey. And we compare the data, the simulated data, with the one from human forecasters, and also realized values. Then we also do a lot of robustness exercises, look-ahead bias diagnostics, right? In these type of exercises, many cases, people raise concerns that the model can already have access to the data you are trying to predict. Right? In our case, we're trying to predict forecasters, if you like, so it might be less likely that the model has that type of data in the training knowledge, but it could be possible, and additional validation. So again, given that this is the look-ahead bias is a concern, I want to address it head-on. And again, the concern is that historical LLM forecast use information that was not available when the forecast was made. So even if we tell the model, so how do we address this issue? One thing we do is that we instructed the model to condition only on information that was available before each SPF survey deadline. Then we also do a recall test, that is, we ask the model to recall realized macroeconomic values. So, and we find that for several variables in the sample, there is the model performs poorly in terms of recalling, even though in terms of forecasting it does a good job. We also do an unexpected events test, that is around major unexpected events. AI forecasts do not become abnormally accurate, as would be expected under look-ahead bias. And finally, the most convincing way to address this is to do a genuine out-of-sample validation. So we evaluate the forecast beyond the model's October 2023 knowledge cutoff for the year 2024, and we find no statistically significant break in the forecast error for most variables. If you would like more details, please, I'm going to proceed, but if you would like more details on this, please let me know. So what are the main findings? AI forecasters replicate broad patterns of the SPF data in terms of median forecast level, forecast accuracy, and features of the cross-sectional dispersion. But they also exhibit departures. In particular, they are less dispersed. So in terms of disagreement, they are not as dispersed as humans. And also we looked at the updating, so regressing forecast revisions on forecast errors and distance from the median. And we find that they put more weight on consensus than forecast error when updating relative to humans. Also, we do exercise to understand what drives the performance, better understand what drives the performance of the model. And we find that providing data actually enhances the performance. So our interpretation is that LLMs could complement traditional surveys by providing measurement at higher frequencies at lower cost, but again, the key is that complement, not substitute humans. Yes? Okay, sorry.
Okay, I was just sort of wondering, what is the objective here? It could be one of two things. It could be actually getting high-frequency, accurate forecasts, or mimicking the surveys with their inbuilt biases at high frequency. It sounds like you're doing the second,
yes.
But you...
Yes.
I would have thought you wanted to do the first.
The first, it's a harder problem, of course, and it needs much more work than just the first. So right now we are concerned with the first. Still, they're used a lot both by policymakers and I mean, in economic models, and also to do potentially counterfactual exercises, potentially FMOC communication studies and so on, where at this stage we are interested in the first. For the second, there are, by the way, some studies, but not using, improving the accuracy of the professional forecasters, right? So just using some other models. That could be a steps for future research, but we will need to enrich the framework quite a bit. So we proceed in steps. Yeah.
And so my question was, how can you make sure that, because these LLM, they are trained injecting a lot of information.
Yes.
So then some of these people who are service analysts, that they kind of write also other piece of information that they can still get embedded into the information the training set. So how do you kind of clean that up?
No, the main thing we do here is this is related to the look-ahead bias, right? So these were the steps we did. The one that maybe would address your comment the most would be the genuine auto-sample, right? Where the model has knowledge until October 2023, and we simulate afterwards, right? But that's not perfect, because this is stuck in the odds against actually the LLM, because the LLM wouldn't have time, unless we modify, of course, the framework, to these real-time data that professional forecasters have access to.
Well, basically, I see every forecast of each surveyed person or institution,
So we don't know what kind of data the model is trained on. So we don't know, for example, if it has, in addition to the macroeconomic variables for which we did the recall test, right? And it does a poor job at recalling many of the variables, right? We don't know if they also are fed the individual forecasters' forecasts as well as the medians. That one we don't know, but I mean, that's the best we can do at this stage. That's what we're doing. I'm going to show the recall, if you are fine with it, unless you would like to see now, with the recall test, we can show you that they miss many, yeah. So in terms of related literature, there are three emerging, in terms of most closely related literature, three streams that are, and it's also going to your question. So there is literature that looks at, that studies whether LLM can approximate human behavior in strategic interactions, for example. And they compare the simulated data with data from laboratory experiments, for example, and they find, in some cases, the model does a good job, is human enough. If you like, in other cases, there are departures. When there are departures, it seems that the LLM is more cooperative than humans. There is a second strand looking instead as a forecasting tool for macroeconomic variables, asset prices, earnings, and financial markets. And they find also some promise and some limitations of the model. And there is finally a third strand that focuses instead of simulating expectations, and that's the one where we are more closely related to, and have been used to generate households, CFOs, firms' expectations, and to study how they respond to information, communication, and narratives. So our contribution relative to this literature is that we focus on professional forecasters. We use LLM to simulate SPF panel, using personas different information sets, and we validate against human SPF and conduct counterfactuals.
So just a quick question.
Yes.
I just want to make sure I understand. There's nothing intrinsic about the LLM here, right? I mean, you could use another model to capture these personas and so on. You could use a state space model or a dynamic factor model, et cetera.
Yes, you could do, but for our case, what we're interested in is creating this panel that potentially you could also do counterfactuals, change information, so on, ask reasoning, for example, why did you provide this type of forecast, and so on and so forth. And we can also benchmark against the models you have in mind. That's another, yeah.
No, it's just that, I mean, you know, at the end of the day, the LLM is a neural network, you know, it's just some model.
Yes, I agree that we could benchmark, yeah.
Which you just described, there are a lot of interesting aspects, but it has big downside potentially also in that, you know, you might tell it don't use any data after 1990, but how many times have you had LLMs lie to you? I've had them lie to me many times.
Yeah, but actually, in a sense, this I see an advantage that we could compare somehow our simulation to your models, to also to some of the models you propose to also, I mean, there is, yeah. So the SPF, I give a quick background of the SPF. The SPF is the oldest quarterly survey on macroeconomic expectations in the US. Was launched in 1968 by the American Statistical Association and NBR, and conducted by the Federal Reserve Bank of Philadelphia since 1990. This is widely used by policymakers and researchers, so people are interested in the insights of the professional forecasters. In this paper, the data of the segments that we use are from 1999 to 2023, because since 1999, the Philadelphia Fed started to post information about acknowledgements about the professional forecasters, which we use to create the personas. They provide here point forecast for 23, what we use point forecast for 23 variables at different horizon lengths. And they are divided in three subcategories: US business indicators, real GDP and its component, and consumer price index and personal consumer consumption expenditure. So this is an example of the instrument that professional forecasters fill out. And I'm only reporting here the first two subsections, and it's for quarter 2 of 2024. The reason I put it here is also that, as you can see, so this is quarter 2 of 2024, the professional forecasters are supposed to put the nowcast, so their forecast for these variables, right? Here on 19, there is the subsection with the CPI. So the one quarter ahead forecast, 2 quarters ahead forecast, and so on. And as you can see, there is here, there is pre-filled data, and this is the most recent data. And that's also what we feed to our model, by the way. When I say we're going to give the model some data, we give the data that professional forecasters have also access to. Continuing on the background, it consists of around 40 rotating panelists, experts from forecasting firms, banks, or other financial institutions, and academia. We don't know, we know some, but not too much about exactly what kind of process they use to provide forecasts. We know that they rely on quantitative models, but use also their judgment to interpret model forecasts and adjust for current conditions and recent trends. Individual forecasts are kept confidential. However, published surveys include the names and affiliation of recent contributors. And more information can be found on the website of the Philadelphia Fed. So here is an example of the acknowledgement for one of the quarters. I'm showing it because that's what we use to create the personas. And also here you can see that people, that forecasters come from different institutions, some from banks, and like Goldman Sachs, Yanasius from Goldman Sachs, and some from academic institutions like Georgia State, and so on. So we use this to basically back out their characteristics, okay? So we integrate this data, the publicly available, and the collected data, so the link in their personal website and so on and so forth, and we create this persona. Basically, we find out what their education was, job title, affiliation, degree, professional role, their experience, location, or sector, and also whether they are social media participation or not. And we find there is some heterogeneity in characteristics and sectors. In terms of education, they're mostly PhD, but there are also some masters, and mostly come from economics and finance. But there are also business and management, and also in terms of other characteristics, there is some heterogeneity. Then we use this information, right, to prompt the model with personas. Okay, so education, job title. I'm going to show you the prompt, actually, exactly how it was constructed. Then we also provide data, the model with the data, meaning the real-time macroeconomic data, which is what I showed you in the instrument, and the past quarter median SPF forecast from the panel. And then we ask for point forecast similar to the SPF instrument, and here just we use ChatGPT-4 Mini with temperature 1, but we also did some robustness analysis with other models. So here is the prompt. So the first 4 lines are about the personas. So we give the model information about the personas of the professional forecasters. The name, the alma mater, education, and so on and so forth. Then we tell the model we are in date Q. Yes?
Just a clarification, are these personas fixed over time?
No, we change because they are not always the same forecasters in the panel.
No, but for a given forecaster who has to fill out the form, is the persona fixed? It's like, or are there time-varying characteristics?
I mean, we keep, no, that one is, we don't change over time. So if the same Yanasius is forecasting in quarter 2, quarter 3, quarter 4, we do not change. My understanding is that we do not change persona. Yeah. Yeah. So if the person changes, I mean, the idea of the person, Yanasius is no longer in the acknowledgement, we don't have it. But as long as he's acknowledged, we have. Yeah. Okay, so we are in, my understanding is that you were asking when is fixed, right? When is always the same, yeah. So we are in quarter 2, let's say, of 2024, whatever quarter it is. You are about to fill out the forecast form for that quarter. Use only the information available to you as the release date. The release date is the deadline by which they are supposed to submit their forecast. Please provide your best numeric forecast for the following variables, and we have the list of variables. And do this for the following quarters: T, T plus 1, T plus 2, T plus 3, and so on and so forth. So basically similar, trying to mimic as closely as possible the instrument of the professional forecaster. You have the most recent real-time data on key macroeconomic variables available to you, and this, again, we extract the data from, as they have it from the instrument. And we give this other one. So here, we give also the previous quarter median for all the variables. Do not incorporate any data that was not available to you beyond the current date, but we do tell the model that it could consider all relevant information of the broad economic conditions and current Federal Reserve actions. Use available information, your professional judgment and experience. Your forecast is anonymous. For each variable, provided the forecast as a sequence of numerical values in the following format. So that's the prompt.
So just to
yes.
clarify, the data that it's using is the actual vintage data?
See, the data that it was in the instrument, so without revisions, right? So the data, yes, yeah.
Okay.
Is the one like I showed in the instrument. Okay, I'm not going to go back. So in the instrument, there was the data, the real-time data, the previous quarter data. Yeah, that's the one that they have. Yeah.
Okay. Just one sort of point. There's at least one way, I think, where the future is obviously slipping in, and that is the LLM was actually trained on the full data set. So all of the weights, all the parameters, that it's using are using the full data set, right?
Yes, I mean, we don't know what's in the data set. Presumably there are some variables. The way we
it
address,
was trained, from A to B, and you're starting in the middle of A and B and then moving forward. But it's using weights that we're estimating using the full weight of B sample.
Yeah, this is the issue of the look-ahead bias. So we did the recall. Yeah, we did the best we could do. Again, with auto-sample, we have a bit over. Are you satisfied with at least the auto-sample stuff? Because for the auto-sample, where the model supposed the knowledge cutoff is October 2023, if we ask the model to forecast 2024, right, it doesn't have. Right, yeah. So we do that. We do that also.
So you're actually using a forecast period.
We do that. Yes, we do that. We do that. But it's few quarters.
Yeah, right.
So we do that, so it's not as powerful as we are extending it. But we also do that in addition to these other things. And also we do the recall, where we ask the model to recall the data, and it doesn't do, for several variables, it doesn't do a good job. Okay, maybe I should jump directly there to convince people, but I also want to show what we do. But yeah.
On the few quarters part, my co-author Asaf has these models that are chronologically consistent. So he has GPT trained in 99, 2000, 2001, etc.
Yes.
So it feels like a very natural use case here to extend your out-of-sample period, so you don't have all these caveats.
Yes, we could do that. But the models typically are less powerful, those models. But it makes sense to have it at least, yes. There are basically smaller models that you can have more control on the training knowledge. We could do that, yes.
So many of these LLMs give different answers, even if you give the same prompt.
Yes.
Just like to do this once, or do you
So, yes, this is a good question. So for this, we did once per persona. When we do generic, we have several. The results do not change much. In another project, I did this, what you are suggesting for each actually firm persona was there. We did several runs and we got similar results. But yeah, but also, yeah, it's in terms of different models, also different models might give different answers. We did some robustness with other models, yeah.
When you give this, like kind of like in a survey, you get an answer, but do you like prompt it again asking like, oh, have you used data from outside?
Yeah, that's a good idea. We didn't ask directly that, but importantly, we asked for the reasoning, why they provided the number they provided. And if I have time, I'm going to show you the results from this analysis. I think there is much more that needs to be done in that area. So in terms of results, this is a large data set, right? Because we simulate the whole panel from 1999 to 2023 and then 2024 as well, the auto sample. And for 23 variables at different horizons for both human and AI forecasters. So here I'm going to show you some results for 4 key variables. The insights you gain from the other variables are broadly similar. So the 4 variables are real GDP, unemployment rate, CPI inflation rate, and the 3-month T-bill rate. So let me show you first some figures of the medians. The median's forecast for the human and AI for the 1 quarter ahead and 4 quarter ahead. So the upper panel shows that for real GDP, the lower panel for unemployment. The thick gray line is the median forecast of the human panel, from the human panel, AI from the simulated. So, and the grayed out areas here are areas of recession. So as you can see in terms of median for the real GDP, the model does a reasonably good job. For unemployment, does a better job at 1 quarter ahead than rather than 4 quarters ahead, but they're still, yes.
I think it would be easier to see the real GDP if you did it in growth rates
Okay,
rather than
yes.
level, because the level, the trend just
Okay,
obscures
yes, we
everything.
can, yeah. And then this is for the T-bill rate and CPI median forecast. Again, for T-bill rate, for the 1 quarter ahead, they're closer than the 4 quarters ahead. Again, these are just the simulated values. And for CPI, which tends to be more volatile, we see bigger departures. So in general, in terms of median forecast, we do find that they're closely aligned for GDP and unemployment rate. But there are some departures also for real T-bill rate and CPI. Yes?
Just going back to those graphs, I wanted to make sure I understood.
Yeah.
Does it seem like the AI forecasts are kind of shifted like a quarter back, like they're lagging the human forecast systematically?
We didn't do a precise test, but here I don't think that there is some lag here, right?
Maybe it's just the thickness of the
Yeah,
line or something.
yeah.
I'm misunderstanding.
Okay, but we can take a look at.
Another thing
Yeah.
that is interesting, so Hal White used to have this insanity filter, remember that, because early on they didn't have very sophisticated techniques for training neural nets. It looks like you have excess volatility, if I'm interpreting this right. I mean, the AI-generated, let's see, CPI, median forecast
Yeah.
is very volatile after 2020 compared to the human forecast, right? So
Yeah,
it's,
but yeah.
those are big differences, right? I mean, several
Yes,
percent.
yes. But it's also not as volatile as they realized. In some cases, it's not as volatile. Huh?
It shouldn't be.
Yeah. But it is more, yeah.
But you're just training it to replicate, not the realized, right? But the actual.
No,
target.
yeah, we don't give, yes,
So it actually,
yes.
the target is actually the kind of like the smooth line here, the human line, right? And it's you have excess volatility relative to that target.
Yes,
right?
that's true. So, yeah, why it's for CPI and not other variables, it might be that the model in the training data is some information that CPI tends to be more volatile than other variables. We don't know. Yes.
Is the AI forecast better at predicting the actual true value?
No, no. I'm going to show you the accuracy. I'm going to show the accuracy. Actually, the mean absolute error we're going to show, but they are comparable for many values. So we don't find an advantage of human, or yeah. So in terms of median, overall, they do a reasonable job. For cross-sectional distribution, however, there are bigger departures. So there is some overlap, but both AI and human forecasters exhibit higher disagreement at longer. So the commonality is that there is overlap, and they both exhibit higher disagreement at longer horizons, which we don't give any information in the prompt about, right? But, however, human forecasters tend to exhibit higher disagreements. So human forecasts tend to be more dispersed, more heterogeneous than the ones provided by the model, even despite the fact that we provide personas. Going now to Andrew questions, what about accuracy? We looked at the mean absolute error for human and AI. So here, I'm going to report for the nowcast, 1 quarter ahead and 4 quarters ahead. And we did randomization tests. So here is for the 4 variables. So as you can see, for real GDP, actually humans, when you see the blue, it means the p-value, right, that the result is significant. The humans tend to be more accurate than AI. For other variables, we do not detect a difference. And here, just in case I show you all the variables, I know it's a big table, but just to show, basically when it's blue, AI it means that humans are more accurate. When it's red, AI is more accurate. So we can see in many cases there is no significant difference, and it's mixed. Sometimes AI is more accurate, and sometimes humans are more accurate. So we interpret this in terms of, here just to summarize, we interpret this as the high performance being comparable with professional forecasters. Yes?
Do you have like another benchmark to compare those numbers to? For example, like in the prompt you're giving it the previous quarter's GDP, for example. Like how comparable is this forecast to an AR?
So we did the exercise with AR, actually in terms of the accuracy, and we find that it's not just doing basically this AR1 process. We have the results in the paper. We can talk more about it later. But the idea of adding more data, we thought about it more, just the previous median forecast, maybe providing more. So in terms of robustness validation, again, we ask what might be driving these results, right? So they do approximate some patterns of human forecasters in terms of consensus, at least. So here we provide the model with personas. We provide the model with real-time data and previous quarter median forecast. So here we kind of do an experiment within the context, again, of this panel. And we ask what happens if we progressively remove this feature. So what happens if we remove personas? Does the model performance change or not? What happens if we remove real-time data, and so on and so forth? The personas and real-time data, previous quarters. So we do that. We also, again, address, in terms of validation, the role information leakage and recall. We ask whether the model can recall. We have the auto sample. I'm going to show you some of the exercise. And also as an application, we compare, we look at the reasoning answers, and we compare to some results of the ECB. So where the ECB asked the forecaster to what extent they used model or judgment. And we use our classification and map into that, and qualitatively we find similar results. So let me tell you about the impact of personas and data. So here, what is this table doing? This is looking at the relative accuracy of AI forecasts with the varying levels of prompt information. So basically, this here is reporting the average relative accuracy of the generic, so the prompt without the personas, versus the original model with personas, data, and median. Okay? And values above 1 indicate worse performance of the model than the baseline with full information. And we again do randomization tests to evaluate whether values are significantly different than 1. So again, generic forecaster basically is the same prompt that we used at the beginning, except that we remove from the prompt the information about their personal, their characteristics. The generic without real-time data, we remove both from the prompt the information about their characteristics and also the real-time access to the vintage data. And the generic without real-time and past SPF, it has none of that. Okay, so these are these 3 columns, again, nowcast and 4-quarter side. The recall exercise, instead we specifically asked the model, we are in quarter 2 of 2005, what is the real GDP value, let's say, what is the value for each variable in this quarter? Okay? So, that's what so what do we get from this? We see that in general, I mean, it's not always, there are some cases in which the performance of the model improves relative to the benchmark, to the baseline. But in general, we do find that errors go up, especially for some variables. Some of the real variables are the ones for which, when we remove information, and also we ask the model to recall, it doesn't do a good job. These are some other examples. Again, we see that, and sometimes the errors are much larger, actually, right? The ratio of the errors is much larger. So this is for, for real time, if you see for real variables. So what I would like to say here is that even though the model does a bad job at recalling, its performance in terms of forecasting, though, it's not as bad. So it looks like that for recalling is not forecasting, okay? So what's the takeaway here? The LLM's performance deteriorates as we remove context. Personas do not currently have a large impact, so the persona do not seem to create a large impact. There is some deterioration with lack of real-time data, but the biggest deterioration comes when we remove the past SPF median. So again, we interpret this as the LLM capturing some common component of expectation formation, but not the individual individual judgment of forecasters. We also find a big,
Sorry, just, I mean, half cheeky, but how specific can you be here with the persona? Suppose that I take away information about somebody having a PhD in economics. Does that improve the forecast?
No, unfortunately. No, we looked at that, with the.
I was just wondering.
I'm wondering even for real forecasters if anybody has done that, right?
But I mean, Jan Hatzenius from
Jan Hatzenius,
had a fantastic post-COVID forecasting record for US GDP, right? I mean, he has an Oxford PhD, worked with David Henry. So can you actually nail what makes his forecast so good?
Ideally, that's where we would like to go, right? Exactly. Figure out, but that's where we would like to go, but we're not there yet. Indeed, is the idea of resuscitating even maybe people who are dead, right, who were performing well. Maybe we can bring them back, but we're not there. But Natsu is funny because okay, I'll tell you later the story about Yana because I only have 5 minutes. So results cannot just be attributed to memorization. So maybe I show you the auto sample because it might be the most convincing so again, we asked the model to forecast 2024, where the knowledge cutoff was October 2023. So the model shouldn't have access to the data. And we did a regression here where we regressed the absolute forecast errors on a dummy variable of whether It was after the cutoff or not, and we do not find strong evidence, right, of a break there. And also here we did, again, randomization test, looking at errors before and after. Sorry, this is all the auto sample, using only the data for 2024. And except for the real GDP, where the humans does better, and we do not find, okay, for the 2 quarters ahead, we find also some evidence here. But in general, the performance of the model doesn't decline dramatically. Even though, again, here we're stuck in things against the model, because we're not giving the model. When we did this, at this stage, we didn't give the model the type of information that professional forecasters have. So, for example, take Q4 of 2024. We had elections, announcement of tariffs, interest rate cuts. So we didn't do that. Indeed, there we see a bit bigger error, but that's where we could try to go back to the model, feed only the news that might be relevant, and check how it performs. So, oh, it went to the beginning. So the final thing, I have 2 minutes, maybe I just tell you about it. We did a validation based on reasoning. So again, a potential advantage of AI forecaster is that we could ask for reasoning. For example, provide a brief explanation for your forecast in 1 or 2 sentences. And we classified the responses of the model into 4 categories using keyword frequency. Whether the model referred to trends, historical patterns, mean, we classified as mechanical, or economic models and relationships, structural model, we classified as model. And if the model referred to Federal Reserve actions, fiscal and monetary policy, or events, such as the pandemic, definitely, we classified as policy and event. So, of course, the big question is, do these align with forecasters? We do not know. We don't have the reasoning of forecasters. But since 2008, the European Central Bank has conducted special surveys at about 5 years intervals to better understand the processes and methodologies used by professional forecasters. And in these special surveys, they do ask what kind of models they use, VAR, machine learning, they do ask all these questions. And they also ask whether they use model and judgment, or where in the instrument they say you should interpret model as any mathematical representation of relationships between economic variables, and judgment we mean experience and intuition. And in these surveys with real forecasters, they find that they use both, which is not surprising, they both use role judgment, models and judgment. But during times of economic uncertainty, such as pandemic and financial crisis, they find that the role of judgment increases. And we aggregated our categories to more closely approximate the ECB aggregation. So the responses in mechanical and model, we classified as model-based, in policy and event as judgment-based. And we do find that also in our simulated panel, the role of judgment tends to increase during, they also use both, but they tend to increase during crisis and uncertainty periods. So conclusion and future work, this off-the-shelf LLM-based synthetic forecasters approximate some key patterns, and in particular the central tendency of professional expectations, but they're also under general disagreement and are more consensus anchored than human forecasters. So our findings together with existing studies provide a proof of concept that they have the potential to enhance current survey expectations data, but there is much more work needs to be done. And here are potential avenues for future enrichment of the framework. Thank you.
Great. Thank you very much. Just a very quick question, we can take it while the next speaker gets set up. All right, there's plenty of time to talk to the speaker in the coffee break. So we move on to the subjective
All right, thanks a lot for coming, everyone, and then thanks for the organizer for including this paper. This is joint work with Jose, and then we are both graduate students at Northwestern. This is pretty much working in progress, so any comments and suggestions would be super welcome. So this paper is about anatomy of subjective macroeconomic expectation. It's motivated by the fact that if we think about expectation formation, we all know that expectation formation are central to economics. And then especially in macroeconomics, expectation formation manifests itself in belief co-movement across many macroeconomic variables. For example, if we think about rational expectations, then whenever there's a perceived supply shock, for example, you expect unemployment to go up and then also inflation to go up. But then at the same time, expectation co-movement also remove many other subjective models or information frictions. For example, if you think about some people have more information about supply shocks, then you might expect their co-movement of macroeconomic expectation to be such that whenever there's an increase in expected unemployment, you might also see an increase in inflations. But it might also reflect other stuff, for example, just differential experiences, and then that gives rise to subjective models and so on. So what we do in this paper is to move beyond isolated forecast error and trying to study joint macroeconomic expectations. So that's exactly what we do. We try to provide a quantitative anatomy of disagreement in households' joint macroeconomic expectations. So what we exactly do is to provide a framework for exactly that. But more concretely, what we do first is to remove the aggregate components to only focus on disagreements. And then after that, what we have is for each individuals, a vectors of macroeconomic expectations. What we'll then study is the covariance structures of that thing and trying to recover latent belief components. We soon realized that it has a lot of similarity with structural VARs because it's pretty much just a covariance matrix across macroeconomic variables. What that means is that we can borrow tools from structural VAR, using it to identify people's latent components that give rise to differential beliefs. So since we have very similar structures to structural VAR, we also have very similar problems. So what we then need to do is to impose economically reasonable assumptions to recover the latent components. We'll tell you much more about it later, but what we specifically do is to use sign and narrative restrictions. And for example, for narrative restrictions, the event we'll be using is mass shooting events. So just a preview, like for example, if people experience some mass shooting events, maybe they are more pessimistic and so on. So after identifying all the latent components, we can use it to do something that it's hard to do otherwise, which is we can use it to decompose the belief co-movement that we see in the data. And then we can ask, who are these people? Who are the people that have certain patterns in the data? For example, maybe their belief looks a little bit more supply-like or demand-like, and so on. And then we'll try to see what this component says about their expectations for other variables or other personal experiences. Any questions so far? All right, so I'll tell you a bit more about the components first before going to the preview of the findings. So the starting point is that we know that households' expectation formation is quite rich. For example, it can be coming from dispersed information, different people having different informations. At the same time, it could just be coming from people having different subjective view or subjective model of the economy. Regardless, that gives rise to heterogeneity in joint macroeconomic expectations. With a rich set, what we try to do is to boil it down to some economically interpretable latent components. Specifically, what we are doing here is to boil it down to supply, demand, and pessimism. So supply and demand is pretty much just motivated by economic theories. For example, if you have idiosyncratic perceived increase of supply shocks, then you expect a higher unemployment and higher inflations. And for example, that's what's documented by Kobe and Gornichenkov, what they call supply side view. Similar for demand, if you, for example, have idiosyncratic belief about innovation in aggregate demand shocks, you expect higher unemployment to go up, but then at the same time, lower inflations. The last component is pessimism, which is a little bit more unconventional. And the reason is that first, when we look at the reduced form, it's quite robust that there's a pessimism component in belief, in the sense that whenever people expect something to be bad, they expect everything to be bad. For example, whenever they expect unemployment to go up, they also expect inflation to go up. That might be making sense. But they also expect taxes to go up, government debt to go up, stock market to go down, so on and so forth. That's also motivated by recent works, reduced form works, that shows that pessimism seems to be important, by this paper by Tobinski et al. And Bodello and Schleifer and co-authors. So each of the components, and we'll show it more formally in the data, you can think about it as just coordinates in the belief formation system. And they reflect both incomplete information and subjective views. So in the paper, we have a more formal framework talking about what these components are and what class of model encompasses. A quick preview of the finding. What we find is that pessimism is quantitatively quite important. So if we look at the variance decompositions, it accounts for the majority share of the positive co-movement that we see between unemployment and inflations. So for example, many people said that it seems like households have a supply-like view or supply-like subjective model. What it seems to be happening is that it's mostly pessimism. And then we are asking further, who are these people? And what we find is that the people that are pessimistic are the ones that have poor health, that has worse financial experiences, that had volatile income process in the past, and then if they are pessimistic about all macroeconomic variables, even the one we're not using to identify the components. And then they also expect themselves to lose their job in the future, have higher default probability, and have higher earning risk going forward. And then the people that have a demand-side view are the ones that are highly educated, especially the one that has graduate degrees. And the people that have a supply-side view are the ones that are older, have greater lifetime inflation experiences, and also not in the labor force. All right, so please. Perfect. So exactly what we'll be using, I'll talk much more about it later, but exactly what we'll be using is tax expectation to distinguish between supply and pessimism. Preview of that is that if you're pessimistic, you might expect, for example, whenever unemployment to go up, you might expect taxes to go up as well. But for supply, it seems a little bit unreasonable, and we'll talk much more about it later, but thank you. Yeah. Very quickly on the contribution of the, in terms of the literatures, what we do is to provide a framework to study the joint co-movement of expectations. And what we try to do is to bring structural VAR type tools, and then you will quickly see the similarities to this kind of expectation data, and then use it to do something that's previously hard to do, for example, variance decomposition. Any other questions? All right, then on to the structural econometric frameworks. So what we do is the following. Suppose that, for example, in one region, say the entire economies, you have n households, and then for each household, you have a vector of belief, BIT. So think about the BIT as unemployment expectation, inflation expectation, taxes expectation, government debt, so on and so forth. So B is a vector of dimension G. And then the B has two components. It has an aggregate component and also an idiosyncratic component. So the idiosyncratic component has two things. There's epsilon ITs, who are the idiosyncratic belief components, and it maps to BIT, your belief, through a structural mapping gamma. And this is exactly the object that we are interested in, the gamma here. So we are not assuming for persistent components for two reasons. First, because in the data, like for household surveys, you pretty much see them for like 3 or 4 times. And then once we remove the individual fixed effect or permanent heterogeneity, there's very little serial correlations. But in future work, we want to extend this to kind of have like individual level VAR. But for now, belief is functions of both the aggregate components and also idiosyncratic components. And then we are assuming that the components has mean 0, and then they have identity covariance matrix, and also have full rank. So these are pretty much normalization assumptions. We are not forcing everybody to load on the common component on the same way, but it's just that the heterogeneity will be showing up in the epsilon IT. So think about this as the mean of the like the mean expectations. Okay. Go a little bit deeper into this. So your belief vector, BIT, again, is the functions of the aggregate components, so think about this as the mean, and also the idiosyncratic component. So gamma, the structural mapping, and then epsilon IT, which are the idiosyncratic component that we're interested in. Some concrete examples. So BIT is just a vectors of your belief. So your belief about unemployment, inflation, government debt, so on and so forth. Please. Yep.
But there's no loading on it. It's just everybody responds to it the same way. So you're capturing heterogeneity with epsilon IT gamma?
Yeah, exactly.
What is the rationale behind it?
The rationale behind it is that we can think about this as the mean forecast. And this is kind of, so aggregate component, we can also think about it as we are isolating out the disagreement components, which is the second part. So what we try to do is to take out the mean.
Okay.
It's just demeaning.
It's pretty much just demeaning, exactly.
And if you have any loadings that are not equal to 0, that goes into the second term.
Exactly. Thank you, Alan. Yeah.
Maybe on the previous slide,
Sorry.
the identity covariance matrix for the epsilon, does that rule out clusters of individual respondents? Like high education people tend to react a certain way, lower education tend to react a different way, but within those clusters they're correlated? Is that ruled out here?
So if it is demeaning, then the error will go to that cluster.
So that would go into the...
So what we are assuming is this is to us a normalization, and what we are exactly interested in are who are these people. So for example, once we get the components, we are trying to see, like for example, if there's clustering pretty much. So yeah.
So maybe another way to frame Cyril's question is that instead of having gamma times epsilon IT, should we have gamma I times epsilon B?
Yes, perfect point. So exactly in the model, we'll show how to collapse gamma I into epsilon, because you can always kind of rewrite epsilon IT such that it includes gamma I. So we interpret gamma I, what you said, as exactly subjective views or subjective models, right?
But you assume that epsilon IT are IB with this identity covariance matrix.
Yeah.
So that already assume away the heterogeneity in gamma I. Right? So often the rationale behind this factor model is that you have loading that characterize the heterogeneity across the cross-sectional dimension, and you have the factors that characterize the shocks across time. But if you make this assumption, then you take the heterogeneity across unit away.
My tempted answer to answer that is no. So you can think about this as, so for example, in the paper, what we do is that you can write down a model where people have heterogeneous subjective models. So in other words, you have different gamma I's, but you potentially also have different information fictions. And you can kind of always rewrite it in the sense that you collapse the heterogeneity in epsilon IT.
This is heterogeneity with respect to the idiosyncratic term. We are talking about heterogeneity with respect to the
eyes, exactly. Okay, well, so maybe it will be a little bit better to, yeah, so one thing that we can do, for example, is to take them at the group level. For example, looking at different groups, and then within the subgroups, we identify the gammas. That's something that we can do, and then we also did it before. But yeah, for now, this is what we have. Yeah, so we are imposing a common time effect pretty much, exactly. Exactly.
And actually in the implementation, I mean, this is just right now for showing this, but in the implementation, we go a little bit deeper on that component. So maybe some of the concerns will be not as...
Okay, so hopefully some of the concerns will be seen more apparently or addressed later. But yeah, for now, this is the notations. And then if we think about that, then each columns of gamma captures how different components move all macroeconomic expectations. For example, if you think about the first component, think about it as demand or something, then it co-moves all macroeconomic expectation in a certain way. Then what we do first is demeaning, so exactly what we are taking out is pretty much time fixed effect. And the rationale behind it is that even if we control for state and month fixed effect, meaning that local business cycle, it only accounts for 6% of the variations. So most of the variations are idiosyncratic variations. That's also kind of a rejection of full information directional interpretations, because under that, you will have aggregate component account for all the variations. So then what we then can do, well, is to write the residualized belief vector as gamma and the structural components. So what we are interested in is the gammas, and what we want to do is to use the gamma, invert the BIT to recover the components. And then we realize that we have the same problem as structural VAR. So what we see in the data is sigma. So we see the covariance matrix. But the covariance matrix only identifies the gamma up to orthonormal rotations. So then what we need to do is to impose economic assumptions on the rotations. Okay, so how do we do that? Well, from gamma to chi, again, we know that we need to impose some assumptions. Specifically, what we'll be doing here is to impose sign restrictions, which constrain how each component can co-move different macroeconomic expectations. But we also do narrative restrictions in the sense that for certain observations, we impose that, for example, you need to have some certain pattern of co-movements. So another way to think about it is for normal VAR, we have time as the dimension, but here we have individual as the dimensions. And once we realize that, we can, of course, also use other identification strategy from structural VAR. So for example, you can think about external proxy. For example, if you know that some people, for whatever reason, have more information about demand shocks in the economy, then you can use that as proxy to recover the gammas. So once we recover the gamma, of course, we can just invert the belief vector and get the structural components.
The sign restrictions and narrative restrictions point identify gamma?
No, set identification.
Oh, okay.
Yes. Yeah. Well, we are Bayesian here, so we'll do it draw by draws. Yes. Yeah. Yeah, okay, so very quickly on the data and reduced form evidence before we go to the concrete identifications and also the evidence. So very quickly on the data, what we'll be using is survey of consumer expectations, where each household just report a wide range of macroeconomic expectations, but also idiosyncratic expectations. And each household appears pretty much 8 times on average, and then the average spell is 5 times, meaning that we only see them on average 5 times in a row. Looking at the raw data, so these are just different slices and different ways to present the covariance matrix. What we do first is just to provide you the correlation matrix. So this is each individual's belief, and then we demean it. So we demean it by state and month. Exactly. So taking out kind of local business cycle effects. After that, what we see is that, for example, if we focus on the roles of unemployment, whenever you expect a higher unemployment, you also expect higher inflation. So over here. Okay, so that seems to be making sense, and that's what people call supply-side view in the literature. But you also see people expecting taxes to go up, and you also see people expecting government debt to go up. So that seems to be hard to reconcile with many of the theory that we have. And if we expand the set, you will see that this is quite robust to all the other macroeconomic expectations. Like, for example, credit constraints, so on and so forth.
So you're merging different subjects, right? For the same person?
Yes, yes, yes.
And are they consistent? Because they're surveyed also at the monthly level. Are they consistent in this?
We are only using SCE, so only one survey.
Yeah, but they are, for the inflation expectations, they're collected at the monthly level.
Yep.
Unemployment also. Are they always positively correlated or negative, like a person internally consistent?
No, not necessarily. And then just like there's the broad patterns. So, but I guess one way to answer your question is are you talking about aggregate, or if we're
Individual, like if I always, you asked me several times, do I always associate positive inflation and unemployment or negative inflation? Or it depends on the time period?
It does not really depend on the time period that we know, because we can, for example, split into different samples, and that seems to be consistent with what we find. I have to think about another way to more directly go to your questions, but yeah, thanks.
So taxes in the previous slide, taxes, yeah, so government debt and taxes are more strongly correlated with inflation than unemployment is correlated with inflation, which is kind of interesting, right? Maybe surprising. 0.389, the last column, and 0.259 is a lot higher than 0.127. Yeah. Is that, I mean, government debt and taxes, are they in nominal terms? And of course, if inflation goes up, then also, or is it as a ratio?
Great questions. And inflation, it's like percentage. Taxes is not. It's tax rate. So the exact question is, holding your income the same as this period, what do you expect aggregate tax rate to be, both federal and local, next year?
And government debt is?
Government debt is the growth of government debt percentage. So that,
Well, that would go up.
that would have inflation,
Yeah.
exactly, yes. Yep.
That's why you get the 0.389. So
Exactly, yes. But I think we also have a version that just do real debt growth, and then was, yeah. Okay, right, so we did different robustness, different time periods, different windows, and so on, and it seems like there's all these adverse directions, adverse components that's existing in the data. Okay, so now we're gonna do a little bit of identification before going to the evidence. So what we do is to first impose sign restrictions. So what we mean here is that the belief vector, BIT, again, a vector of unemployment, inflation, and taxes, we assume that it has, again, the relationship of gamma and the epsilon IT here. So there are three components: supply, demand, and pessimism. And then if you have the supply components, then whenever you expect unemployment to go up, you also expect inflation to go up. If you have a demand component, then whenever you expect unemployment to go up, you expect inflation to go down. For pessimism, if you're pessimistic, you expect all macroeconomic variables, so here including taxes, to be going up. So taxes is the one that help us distinguish between supply and pessimism. Because, for example, if we think about standard conditions, whenever there's a supply shock, you expect either the government would do fiscal stimulus, automatic stabilizers, or if they don't do anything, it's hard to think about taxes being going up. But if you're pessimism, on the other hand, then you would think that everything's going bad, so taxes would go up also in that case. So indeed, if you look at historical evidences, whenever there's big supply shock, if anything, taxes is decreasing. So what we'll be doing is to impose this sign. So we are restricting the gamma such that it has to satisfy this sign.
On the previous slide, you had government debt as well. That's not here.
Great point. The reason why we don't have government debt or other variable is pretty much trying to minimize the set of variables that we have and then to identify the components. We also have versions that have government debts and also, for example, credit constraints. The results are pretty much the same. But then we have to impose more size. So that's exactly why we don't want to do it. But then the results are pretty much the same. It's just that the probability bands will be wider. So complement to that, what we then do is to also impose narrative restrictions. So what narrative restriction means is that we are imposing that for some observations, belief has to move in a certain way. So what we do is, the idea here is to, well, the idea is pretty much that people that have experienced mass shooting events are on average, even though not necessarily all of them, more pessimistic than people that did not experience the mass shooting events. So concretely, the way that we do it is that the treated household here are the ones that live in the commuting zone that experienced, that in the last month or this month had the mass shooting events. And then you answer a survey after the mass shooting event. And then what we are assuming here is that for the people that had experienced the mass shooting events, they are on average more pessimistic than the people that did not experience a mass shooting event.
So we have non-economic events of mass shooting to identify.
Could you say that again, Serena?
So mass shooting is a non-economic event, right? It's a social event.
Yeah, that's exactly the rationale, because we thought that it's not related to fundamental, at least it's not, for example, a supply shock. Potentially it's a demand shock, but we're just requiring that on average, some people is a bit more pessimistic than others.
So in their paper about identifying sentiments using mass shooting, I mean, that wasn't a very strong instrument.
Yes, but it's not a very weak instrument either. So especially in the micro level, because what we are looking at is not the aggregate time series, but rather the dispersions. In that case, it's actually, we do have a relatively stronger first stage. And then the identification assumption is not very strict either, because what we are assuming is just that on average, some people are a bit more pessimistic than the people that are not treated. So when we remove the mean, we remove the state month, so it does have a location. But here is commuting zone, so it's even more granular. Yeah, I'm not very familiar with Massachusetts, but yeah, think about it as the difference between Massachusetts and Boston. Right, so concretely what we then do is to do Bayesian estimation and then imposing sign and narrative restriction at the same time. Yeah, detail of the estimation process are in the paper, but for the interest of time, I'll not be showing them. Okay, so now on to some results. So what we'll first present you is to show variance and covariance decompositions, and then we'll be looking at who are these people that have different components. And then finally, we'll try to understand if you have a supply side view, what does that say about your other macroeconomic variable, other macroeconomic expectations, as well as individual level expectations. So on to the first things. This is just a warm-up. So what we are showing is pretty much the gamma matrix. So on the left here, for example, is what happens if you are pessimistic. So if you have a pessimism component increasing, then you expect unemployment to go up, inflation to go up, taxes to go up. And what it shows here is pretty much the probability bands, and most of them reflect set identification rather than estimation uncertainty, because we have a large number of observations here. If you have a supply side view or a supply component, then you expect unemployment to go up, inflation to go up, and taxes to go down. And then if we look at demand, if you have a demand-like components, then you expect unemployment to go up, inflation to go down. And then even though we are not imposing any restrictions on taxes, you expect taxes to go down as well. So kind of in line with whenever there's recessions, taxes might go down because of fiscal stimulus. All right. So now on to the meat. So if we look at covariance decompositions, so again, we are plotting the same figures, but we are decomposing the covariance, for example, between unemployment and inflations. What we see is that the positive pattern that we see in the data, they are driven by both pessimism and supply, but they're mostly driven by pessimism factors. So 70% of the positive contribution are coming from pessimism, meaning that if people think about a supply side view, it's mostly reflecting pessimism. Same thing is true for the covariance between unemployment taxes and inflation and taxes. Next, what we'll be looking at are pretty much trying to understand who are these people. For example, understand who are these people that are pessimistic than compared to others. What we do is that we regress each component over different demographics. And then we do this draw by draw. So for each acceptable gamma, we do this exercise, and then we'll report you the whole range. And then what we'll be reporting is the predicted means, meaning that we are controlling for other covariates. So first, what we'll be showing you is the anatomy of pessimism. So looking at who are the people that are pessimistic. So here are the demographics. The first one is financial situation. For the past 12 months or so, did you experience bad financial situations? Second is income volatility. Were your income more or less volatile compared to other people? And then health status. Did you experience bad health experiences? Employment status, and also presidential alignment. Are you living in a commuting zone that voted for the current president or not? And finally, income. So what we see is that, the people that had worse financial experiences are pessimistic. The people who had bad income volatility or higher income volatility are pessimistic. The people that are in poor health status are pessimistic. The people that live in an area that did not vote for the current president are pessimistic. In other words, it seems to be the case that pessimism are concentrating among people that had worse financial experiences, poor health, weak employment status. Please. Some of them is consistent. For example, health status, that's one of them. Income volatility. But what we are trying to show is trying to provide an anatomy of pretty much dual variance decompositions of seeing who are these people and who contributes most to the covariance that we see. Yeah, exactly. So, for example, one would expect that after elections, and then the president you voted for actually won, then you expect pessimism to be flipping sides. Yeah, because what we are pretty much looking at, you can think about it as cross-sectional. We are doing cross-sectional identification. So one could, in principle, do this for different snapshot of times. What we are doing here is to pull them together, and that's pretty much the finding that we have.
Just a comment. If I were thinking of setting this up, I wouldn't have this mass shootings narrative, which strikes me as, well, it's not one of the first 20 instruments I would have thought of. I would take some of these things, like people on the losing side in an election become more pessimistic, or people who lose their jobs become more pessimistic. Make that the narrative restriction.
Great point. I think presidential alignment would be a great instrument as well, so we should do that.
I meant instead.
Okay, sounds good. We should do that, probably. Yeah, but income process is a little bit more because you might infer a bit more from, is your firm experience the demand shocks or whatever. Looking at some other covariates, what we find is that people that in their life experience more recessions are also the ones that are more pessimistic. And then the one that spend more on medical spending, so consistent with what we found before, and also spend less on recreational spending, are the ones that are pessimistic. So again, it seems to be the case that pessimism are concentrated among people that are more vulnerable. But then what we then can do is to look at also who are the people that have a more demand-like components than supply-like components. Well, because there's a large number of figures, so what we will then show is only the summaries. The people that have a demand components are the ones that are highly educated, especially the one that has a PhD. And then the people that have a supply view are the ones that are older, have greater lifetime inflation experience, and are also not in the labor force, so they're not working. Finally, what we will be looking at is to think about how does this component affect households' other expectations, so the expectations that are not used to identify the components, and what does it say about other households' individual expectation going forward. So we do the same exercise where we regressed your macroeconomic expectations or idiosyncratic outcome expectation going forward on different components. And what we find is that if you are more pessimistic, you will expect government debt to go up, long-run inflation to go up, inflation uncertainty to be going up going forward, all range of prices to be going up, and for the whole economy, everybody is having a harder time of assessing credits, so on and so forth. So what it seems to be happening is that pessimism is associating with adverse shift in all expectation. So if we look at individual expectation, then we will see that people are pessimistic are the ones that expect themselves to have higher earning uncertainty going forward, more likely to lose a job, just going to be financially worse off, more likely to default on loans, and more likely to spend on, say, essential spendings. So pessimism predicts higher adverse individual outcome also going forward. For that, it's possible, even though when we demean the expectations at the individual level, so you take out the mean fixed effect, the persistence is actually quite small. And that's exactly why we are not doing the individual VAR type exercise. Right, so finally, we're trying to understand, can we say something about aggregates? And then the answer is no, because by construction, we are only looking at disagreement. But we can say something if we make some strong assumptions. So the idea is that we can have the identified set of structural mappings, and then we just apply it to the mean expectations. So the assumption then is that the representative agent form belief exactly the same way as what we identify people forming a belief for individual expectations. So the assumption is relatively strong, so it's also relatively easy to refute in the data in the sense that it might produce you something that doesn't make much sense. So what we do then is that we apply this at each state mom level and then aggregate it up. But what we find is that it actually correlates with first Michigan consumer sentiment quite well. So it has a negative correlation of 0.8. And then if we look at the time series of that, there are two patterns. First is counter-cyclical, and secondly, align with salient event quite well. For example, well, after COVID, there's a big spike of pessimism. And then when inflation hits, there's a big spike of pessimism. And in most recent time, when SVB collapsed, there's also a last spike of pessimism. Going back in time a little bit, when Trump cut taxes, there's a reduction of pessimism, meaning that people are more optimistic. So this is pretty much what we have. So what we do is that we study macroeconomic variable jointly and try to import tools from structural VAR to microdata. We find that pessimism is a variable that explains large share of belief co-movements, and they are concentrated among people that are vulnerable. In the future, we are trying to apply this to other data sets where we can actually have idiosyncratic level persistence as well. So thanks a lot for your attentions and also for all the feedbacks that you gave. Thank you.
We have time for some questions.
One comment. There's a bunch of papers that have tried to estimate things like the Phillips curve in the cross-section of surveys.
Great point.
Like they've tried to say, do the people who predict particularly high unemployment also predict particularly low inflation? So that's an interesting exercise, but that's one that's sort of assuming the nature of the structural shock, that it's only driven by demand shock.
Exactly.
So a way of motivating this is that you're getting away from assuming that the cross-section is exclusively driven by one type of shock.
Yes. Yeah. Thank you. That's a good point.
Questions? Do you have data on survey participants' asset holdings by any chance?
There's a chance. There's actually a modular that has financial asset holding. So yes, actually the answer is yes, but we haven't looked into that yet.
That would be really interesting, right?
Yes.
To see how pessimism affects that.
Yeah. Thank you. Thanks.
Any other questions? Or people are dying to get coffee? That will be served out there, by the way. All right. Well, let's thank the authors and then come back.
Hi, I'm Luca.
Thank you.
Thanks for
Oh yeah, of course.
All right, so we have two papers on density forecasting. So a common theme here, and the first one is from a group of researchers at FRBNY, which you don't know what it stands for, right?
Well, thanks a lot, Alan. And thanks everyone for being here, and thanks to the organizers for including our paper in the program. I'm going to talk about learning from survey density forecast, which is joint work with Richard, Dennis, and Gisem. Gisem is here with us, and Richard and Dennis are not. So naturally, every error that you see is the fault of Richard and Dennis. Before I begin, the usual FED disclaimer applies, so let's take it away. An important feature of many surveys of forecasters, households, and firms is that they ask respondents to report their density forecast. And by this we mean they ask them what is the probability distribution that you have in your mind about the future realized value of some random variable. An early example of this is the survey of professional forecasters, but this is pretty common today, and at the New York Fed in particular, we have the survey of consumer expectations, which is specifically designed to elicit density forecast for things like inflation, unemployment, individual income, spending, and so on. I don't need to tell you how important survey expectations are. When it comes to density forecast, these are particularly attractive because of many reasons, but two of them are they are easier to interpret than point forecast, and they give us a more complete picture of the shape of subjective uncertainty. So there are a lot of nice things about expectations and survey density forecast in particular, but they come with a challenge, and that challenge is what motivates this paper. And to tell you what the challenge is, I need to tell you about the question format that you find in these surveys typically. So what we do when we ask people about density forecast is we take a random variable of interest. Let's think about 1 year ahead inflation, which is the example I will be using today in all instances. We partition the support of these random variables into a small number of intervals or bins, and then we ask respondents to assign probabilities to each of these bins. So the output of this process looks like this. So you see a finite number of bins, some of which might be unbounded, as you see in this figure, and then some numbers that denote the probabilities of these bins. So any person trying to use survey density forecast in their analysis to test an economic model or so on has to confront an important methodological problem, which is how do we map this small number of probabilities into the object of interest, or more generally into the full density as a whole. In practice, the most common approach is to feed a parametric density. The generalized beta is a favorite among practitioners, but it's far from clear that this is the right thing to do. It's far from clear that the densities that we see fitted in practice are information supplied by the respondent, or are the information supplied by the researcher. Also, that's the question. In light of this is where this paper comes in. We are going to study this question more systematically. How do we transform these probabilities into statements, meaningful statements about objects of interest? And we're going to do that in a systematic way. So what's our main contribution? Our main contribution is we are going to come up with a method to construct non-parametric, non-parametric lower and upper bounds for objects of interest coming from survey density forecasts. By objects of interest, the objects of interest that will be covered in our treatment include things like the mean, the variance, quantiles, medians, things like that. And our approach will have a number of desirable properties. Okay. Yes, so number of desirable properties. First of all, we will not need to specify a parametric density. We will not need to say that the data are generated by generalized beta, for example. In particular, we will avoid restrictions on features like the skewness or the number of modes. We don't want to say anything about those. The second desirable feature is that we will be respectful of the data supplied by the respondent. We will match reported probabilities exactly. the third desirable feature is that we will be able to incorporate additional information in a transparent way. The additional information we have in mind here are things like the smoothness of the underlying density or tail behavior. And there is a fourth advantage. Give me a second. Fourth advantage.
Okay, question. I mean, is it related to what you just said? I mean, is it obvious that you want to match the reported probabilities exactly? I mean, maybe a little smoothing could help. And of course, that's what fitting a parametric density would do.
Yes.
I'm just curious how you
That's a great question. So what we're going to do will allow the underlying density to be smooth, and it will allow us to put information on that. So we will not completely forgo that possibility, but we will do it in a different way that preserves the underlying density. What they're saying is that there might be reasons why the reported probabilities are not exactly what the agent meant when it was answering the question, and that requires modeling this process of elicitation. That's not something that we're going to do in this paper, but it's something that we think could be dealt with the tools that we developed here. Anyway, so those are the main advantages of what we're going to do today, and I will spend most of my time, actually, if my calculations are correct, all of my time talking about this. But there is a second contribution, which is in a first step, we use this method to come up with bounds response by response. Each individual gives us these bins, these probabilities. We construct lower and upper bounds for whatever object of interest we have in mind. And we do this for each response over time, for each individual, and so on. In a second step, usually we want to use this to answer another question, usually a more interesting question. So what we do in the paper, that again, probably I will not have time to cover today, is we show how to incorporate these bounded functionals into regressions in the role of either the left-hand side variable or the right-hand side variable. We provide tools to do valid inference in that setup as well. So there is this other contribution that I will only talk very briefly or not at all today. So in terms of where we are located in the literature, these things that we propose are put us in relation to two things. So one is the density question. The main reference point here is Engelberg, Mansky, and Williams, who proposed what they call a hands-off approach that also respects the probabilities but doesn't use within-bin information. The other extreme and the most popular in the literature is to fit a parametric density, as I said at the beginning. What we're trying to do here is a middle ground between those two that we think takes the best from both worlds. When it comes to this last contribution, the regression with interval value data, we connect there with the partial identification literature with set value information. But probably I will not have much time to talk about that. So the plan for my presentation is as follows. I will first try to motivate this problem and give you a bit more information about the actual problem that we're trying to solve. I will tell you about our bounds. I will show you how we implement these and what we learn when we apply this to the survey of consumer expectations. And finally, just one or two slides about regressions with bounded data. So, let's make the data object a bit more concrete. So this box is approximately what a respondent of the survey of consumer expectations sees when we're trying to elicit their inflation expectations. So here the question we're asking is, what do you expect will happen with inflation over the next 12 months? And there are a bunch of bins, and the agent responds. The respondent gives some response that takes the shape of a vector of probabilities. Also, this is pi that you see in the slide. It's just a probability of different outcomes here. The only restriction that we have on pi is that it has to be greater or equal than 0. It has to sum up to 1. And there are mechanisms to ensure that the agent responds consistently, so we can assume that this is what we get there. We know nothing from this table about what happens inside each bin. So within each bin, we don't have any information. We have information just probability of each bin. And that's the key identification problem, so to speak, that we face here. So let's call the bins AK, and let's call the probability of each bin pi k. What we know for sure is, I mean, again, trusting that these are the agent was truthful. What we know for sure is the CDF at the boundary values of the bins. So this is the CDF evaluated at the boundary value, is the sum of the probabilities of all the bins that are to the left of that value. What we don't know is how probability is distributed within each bin, and therefore we don't know what's the density function, we don't know the mean, we don't know the median unless one of the bins is exactly 0.5, sums to 0.5. We don't know other functionals. So that's the challenge that we have here. So in the literature, there are two extreme routes that one can take. One is the hands-off approach proposed by Engelberg, Mansky, and Williams, which essentially is we explore all the possibilities that are compatible with the data without imposing any other structure. That's no within-bin structure approach. The other is to fit a parametric density like the generalized beta. So what I'm going to do in the next 2 slides is show you a few figures. We took some respondents at random from the survey consumer expectations. We will apply these 2 approaches, and I will try to show you what are the limitations of this and why we want to do something different. This is one of the respondents. Now let's ask the following question. What do we know about the median if we see this? We know that the median must be, so we know the CDF at boundary values. We just check where 0.5 falls. In this case, the CDF at 0 is 0.37, CDF at 2 is 0.92, so the median has to be in between those 2. So the bounds for the median here on the basis of this information is 0 to 2%. We can do a similar approach for the mean. So the way this goes is, we maximize and minimize stuff over all the things that are consistent with the data. The solution to those minimization and maximization problems is to compute the expectation of a discrete random variable that puts all the mass to the left or to the right of the random variable of the means. And if you do the calculations with this data is applied, the result is as follows. The expectation is between minus 0.8 or 1.3%. So what can we learn from these 2 things? One is the intervals for the mean and for the median are quite wide. So they are about 2% wide. This is inflation, annual inflation, so 2% is the inflation target also. It's very, very wide, a lot of uncertainty. In the case of the mean, we don't know if it's negative or positive for this agent. It's so wide that there is that uncertainty as well. This is a very favorable example to this calculation because the agent that responded to this didn't put any mass on the open-ended bins. So this is all bounded. If she had done that, then the interval for the mean might be infinity on one of the sides or both sides. So for the mean, it might not even be defined as we saw before. So that's one limitation of the hands-off bounds. The summary is, yes, they respect the data as much as can be respected, but it's not very informative typically. It produces very wide bounds. We might want to include additional information. As Frank was saying, one possibility is to fit a parametric density. Here I'm showing you one respondent that put 0 mass on the open-ended bins. So here the hands-off approach for the mean is not even, it's minus infinity to plus infinity, so not very informative. Let's do the following. Let's feed the generalized beta to this data. These are the orange bars. The orange bars are obtained as follows. We feed the generalized beta to this response. And then we compute for each bin the implied probability. So this is what the thing that we're trying to minimize when we choose the parameters of the generalized beta. So what do we learn here? One is the generalized beta doesn't fit the data perfectly, and actually it fits it pretty badly. So there are a lot of deviations from the gray bars, and the orange bars ideally should be on top of each other. They are not. The generalized beta here gives you an answer that I don't remember exactly what the mean was, but it gives you just one answer. It doesn't give you an interval. So there is no uncertainty if we trust that the response looks like the orange bars and not the gray bars. But there is a problem. Even if the orange bars were on top of the gray bars, which is not the case here, there are many other parametric distributions that fit the data equally well, but imply different expectations. So even if we have a model that fits the data quite well, we cannot be sure of that. So it might make sense to consider that range of possibilities, the range of all possible densities that fit the data equally well, that share some properties, some structure, and then look at how the mean, the expected value for X changes in that setup. So that's what we're trying to do here. We're trying to get something that's more informative, that hands-off, that imposes some structure on the underlying densities, but still matches the data as good as well as can be done. Okay. So that's the motivation for what we are trying to do. So let's now put this a bit more formally. But again, the idea is quite simple. It's just there are a bunch of notation and ideas. Okay. So we take one respondent at a time here. So for the rest of my presentation, except for the last 2 slides, that's what I'm going to do. So think about one person here. That person has one underlying subjective density, which is F star. This is the distribution of the random variable X. Also, that's the notation. And then we ask this person to fill in this table that I showed you at the beginning. The result is this D thing. It's A case and pi case. What do we know so far when we see this answer? The pi case are linear restrictions on F. Also, they are these integrals over some sets of the density function. We know the sets, we know the value of this, we don't know F star in that. So these are linear equations on F star. They are functional linear equations because F is a function, but they are linear. what we are trying to do is we're trying to learn about functionals of F star. Those functionals, for now, will be linear in the following sense. So we're going to try to compute the expectation of a function g. The g will be known and chosen by the researcher under the probability distribution implied by F star. So that's our target. This target is also linear in F star, because we know gx. Gx is kind of a vector. It's infinite dimensional. F star is the part that we don't know. So this is like the outer product of those two. So what's the goal here? We want to match the data exactly. You put some minimal structure on F star, and then consider all possible values for this target functional, the theta star. So this is the key slide of the paper. So if the presentation ends now, you will not lose anything. So pay attention to this. We will have the following. We have FD will be the space of candidate densities. This is all possible densities that we're going to consider that are consistent with the probabilistic data. So they satisfy all these linear restrictions implied by pi's and a's. And they are consistent with some maintained restrictions that will include things like smoothness, and I will explain shortly what we mean. And then within that class, we look at the target functional. We compute expectation of g under each f in that class. We look at all possible values, and we take the minimum and the maximum. These will be our bounds for theta star. So what can we say? F star, so every density in FD, is consistent with the data. So we are going to impose that. And second, the bounds will be sharp in the sense that we will not consider any distribution that does not satisfy the probabilistic data, or any distribution that does not satisfy any other information that we think is relevant. For example, smoothness. We will not consider crazy distributions, only distributions that we think belong in this class. So these are the two properties that we're after. So matching the data and having sufficiently informative bounds. Importantly, if FD, and this will be important for the implementation and for many of the ideas, if FD is defined by linear restrictions, so far the restrictions I gave you are all linear, by the way, then these are functional linear programs. So they are not that easy because they are functional, but at least they have structure and mathematical structure that we can learn about. And again, just for the 5th time today, these are respondent specific. There is no cross-sectional pooling so far. So that's the key idea. Let me just say briefly that what we can cover with this idea. We can choose G to match a lot of objects of interest. For example, the expectation is just take Gx equals to little x. And center moment is Gx, x to the power j. The CDF at any point, not necessarily the boundary points, is an indicator function, and so on. So there are a bunch of examples that are already covered by this. There are some examples that are not covered, that cannot be written in this way. We cannot write the variance like this, and we cannot write quantiles like that. But we can provide bounds for those building on these ideas. And I will do that in 2 or 3 slides. Now the space of candidate densities, or the density that we're going to consider. And here's where smoothness will enter, and I think this will be my answer to Frank's question. We are going to consider densities that first have to be densities, so they have to be greater or equal than 0, integrate to 1. They are going to be matching the data, so the integral over a's have to be equal to pi's. That's the second restriction. And then there is a third restriction on the norm of a derivative of this function. So we are going to ask that some derivative of certain order p is bounded in max norm. What we mean here is that when we look at the full support, we look at the places where this derivative changes wildly, and we put a bound on that. And that bound is governed by this number phi, little phi, phi, sorry. And that's the key parameter here. So we index the class by phi because we can consider more or less smooth functions by changing phi. We can also change p as well, no? But that's the idea. So this is yes, sorry.
So here you assume pi k is null. So are you implicitly considering large surveys where the estimation error for pi k is negligible?
So pi k here, we take it as given. So
yeah,
what you mean?
But let's say if you just survey professional forecasters,
yes,
there could be like a few dozens or maybe hundreds. So there, the pi k estimation could be very imprecise. So are you going to take that into account?
Not in what I'm going to show you now. These bounds are not going to take any uncertainty about pi k into account. But there are ways of incorporating uncertainty about them. One concern, I mean, here remember that this is responded by respondent. No? So given respondent, usually we don't ask a lot of bins because it's overwhelming. Here we ask 10, which is already a lot. but typically we have a few bins there. But what we can incorporate is things like rounding. If you have rounding error, you say what they report is within some some quantity of the true response. That's a linear inequality constraint, and that can be incorporated into what we do. So that can be done. But for what I'm going to present, just for simplicity, I'm not going to do that. Yes.
So there's no T subscript here, but I imagine that even for the same respondent, right, you have a time series
Yes.
often there. And one phenomenon that's common in these services is that people don't revise their views at all. And so it's just, pi kt is the same as pi kt minus 1, right? So is it trivial to, expand that to just conditioning on past information and is observed, or
that's a good point. I haven't thought about how to do that, but I think it could be. I mean, you mean using the past information as additional linear restrictions in the program?
Right.
That could be done. It's not something that we have explored, but I think that would be interesting to look at. But the other possibility, I mean, what we have in mind here is we do this for every respondent in every period of time. So the same respondent we will see time and again, or for a couple of months, most of the time here. And then use that subsequently in our regression analysis. That's something that we can deal with what we have now. Incorporating these additional linear restrictions coming from past responses, that's also straightforward to incorporate.
And is there also an intuition in terms of if I give you a more granular classification, so I change the set AK, then these bounds will be trivially more informative in some sense, because we know that these bins are they're set exogenous, but they change over time, right?
Yes. So that's a good point. So what happens when we give people more or less granular bins, or it's not clear, but the way we incorporate information about that is through the smoothness restriction. So ideally, if we observe for the same individual in the same period answers to questions with different aggregations of the bins, that should give us information about how smooth the underlying density is. Here we're imposing information on that, so probably it's something to explore, but it's not, I'm not very sure what we'll get from that. No. Yes?
Is there some result that says the identified set for these linear functionals under these linear restrictions is an interval, so you're getting the sharp identified set?
Yeah, it's not. It depends on the G function, I guess. Yes, it's not clear.
Be getting an outer set.
Yes, exactly. Yeah, you're right. So for the mean, it should be an interval, but for complicated G's, it might not be.
So
but still, it's going to be. It's going to be the sharpest outer set, not necessarily the sharpest identified set.
But there is a result for the mean, for example, that says that this is.
For this case, it should be, but yes. Yeah. So let me, but yes, with the caveat that these are outer sets, let me move on. So one other thing here is sometimes some of these objects are not well defined unless we do something about the tails, particularly when we have unbounded G functions. For the mean, for example, this is something that we were seeing with the hands-off approach. So in addition to this structure, when we deal with unbounded supports, we also put some structure on the tails, and I can tell you about that when we get to the implementation. Yes?
So you just used the word tail, so I'll ask. I'm sort of sitting here in general thinking about tails, and the word hadn't even come up. So what do you do on the edges?
It's going to be very important for some functionals, yes.
Yeah, I mean, well, there's the issue of what do you do, I'm not sure yet, but also, in anything like value at risk or expected shortfall, it's explicitly the tails that you're interested in.
Yep.
So I'm wondering, what's assumed or whatever.
Yes, so I can tell you, maybe let's postpone this discussion to when I get to the implementation, so we can talk about the details there. But what we're going to do is we're going to impose restrictions that say that the underlying density is dominated by some known density that decays sufficiently fast. And in our case, we're going to decay sufficiently fast. So it has to decay quickly enough for the expectations to be well-defined. And what we are going to use here are exponential tails for these cases. But I agree, the questions that we are after here, remember, is expectations or variances or things like that. If we are interested in value at risk, that would be a different question, and we would need to think more carefully about the tails.
So why are you looking at the particular derivative and not
all derivatives up to an order? That seems like a more natural notion of...
That can also be incorporated. So this is just a minimal way of introducing smoothness, but yes, you could put all the derivatives up to that order. They are linear restrictions, so they fall into, that can be done. Okay, so this is the candidate space. Now you know the candidate space, you know what type of functions we can deal with. You know that our main idea here is to minimize and maximize to compute these outer identified sets for those functionals. What we are after now is an implementation, because this is a functional linear program. We cannot solve it in a computer, so what we need to do is put something that we can do in a computer. The idea that we're going to use is we're going to discretize the problem. So for now, let's take a bounded support, and I will relax this in a sentence later on. Take a bounded support. So we discretize this support into m different grid points. M is something that we control, the researcher controls. So this is a choice of the researcher, and it will be our approximating choice, basically. And then we discretized F, we replace F by a discrete version. And this discrete version is a vector of probability masses. This is F tilde that you see there. So there will be restrictions. It has to be, each entry in F tilde has to be greater or equal than 0. It has to sum to 1. It has to sum to pi's over a's. And finally, it has to have some smoothness as well that will converge in the limit to the continuous problem. The way smoothness has to be imposed here we have to multiply by h. That's just because f is not f tilde is not proportional to f, is proportional to h times f, because these are probabilities over small intervals. And here we use a discrete derivative for the discretized version. Also, we have discretized everything. We have discretized the domain. We have discretized f into f tilde, sorry. And we have discretized the space of candidate densities. So with this, now we can solve the problem. So by the way, the this space of candidate densities in discrete space, if it's non-empty, it's a polytope. It's convex and compact, so the minimum and maximum are always attained, because also the objective is continuous, no? So that's the Weierstrass. So we compute the mean and the maximum, and this would be the discrete counterpart to our outer bounds for the continuous problem, for a given m. So here we choose m, we solve these problems. These problems are linear programs. They are straightforward to solve, even with a lot of restrictions on the computer, so this is perfectly doable. So how can we justify doing this? There is a theorem, the proposition, not very deep, not very surprising, but we can prove that if m tends to infinity with regularity conditions that are not too crazy, you get convergence of the discretized solutions to the continuous problem bounds. So we can choose m large enough, and we will be guaranteed to be close enough to the bounds that we actually want to use. That's what we have here. Well, that's the idea. So what I want to say are two things, or three things. One is the assumption on G is bounded variation that allows for the moments on bounded support, their bounded variation, and the indicator function of the CDF. So at least those examples we know are covered. A lot of other examples will be covered. So we're not imposing anything like continuity of G or anything like that. Second idea, and this has nothing to do with the proposition I said. So when we can find a minimum phi when we fix m, when we fix the amount of discretization we use, we can find a minimum phi such that we can solve this problem. And below that phi, f, the discretized candidate space, becomes empty, and then there is no solution. So there is always a minimum phi. That minimum phi has an interesting property, which is it doesn't depend on G. It's just whatever phi you get to this space is non-empty. And why is this important? Because this gives you the tightest outer bounds that you can get in this problem. Also, because the bounds are monotonic in phi, one can prove that using like the maximum theorem. This gives you the most information that you can get with the discretized problem. In the continuous problems, phi can be very close to 0, so it doesn't so much sense to look at this, but this is a reference point, because you cannot get more information with a particular derivative restriction than the minimum phi. Let me skip that one, but let me say this. This result extends to an unbounded support. What we would do is we need to truncate, impose some tail structure, and then let the truncation go to 0. Eliminate the truncation asymptotically, and then you get the same approximation result. So essentially, what you need is to make a very refined grid to approximate the continuous problem very well, to let the support grow over the approximation to cover most of the probability action that's going on. So that's what you need for this to work with unbounded support. Okay, so very briefly, I want to say we can also deal with the variance. So when you have objects like centered moments, things become more complicated because these are no longer linear in F. They are nonlinear, usually polynomials for this type of problem. So instead, and these are hard to solve even after discretization. So in the computer, this is very unpleasant to deal with. So instead, for these centered moments, what we suggest to do is to solve the problem sequentially. Usually what you need to do is approximate the mean. You end up with an interval for the mean. And then the problem is linear in the outer F1, in the outer density that you're using to compute the integrals. So it's two linear programs that are solved many times instead of one complicated polynomial program. And this is also straightforward and fast to do in the computer. And we find that these bounds are valid, but they are going to be conservative. In practice, they don't seem to be extremely conservative, but they are more conservative than solving the complicated polynomial problem. The same works for skewness and kurtosis coefficients, so this approach can be adapted more generally. For quantiles, we can use the bounds on the CDF to bound the quantiles. And the way it goes is we bound the CDF, we create an upper and lower CDF envelope. That is, for every x, we compute these upper and lower bounds using the approach that I described at the beginning. And then we do the inverse of that. So the upper bound for the CDF is the lower bound for the quantiles, and vice versa. That's what we have here. Again, straightforward to implement. Everything's linear, can be solved in the computer, and we can also apply this to interquantile ranges or quantile-based measures of schemes. Also,
what drives, again, to go back to the tails.
Yes.
You know, maybe you want a quantile that's way out there, as people often do. I mean, I guess that would be notoriously hard to estimate with any precision. But moreover, I guess it's going to depend on the assumption. I think you said you make an exponential dominance, so it'll come off that.
Yeah, I agree. So if you have a quantile that happens to be in the unbounded intervals, then everything will depend on what you do with the tails. If you have something that's in between, you don't need that structure. Actually, you don't need tail structure for the problem because G will be bounded in that case for the CDF. So it all depends on whether you're looking at the tails, like in value at risk calculations, or you're looking at something in the middle. The thing we had in mind here when we wrote this was the median, actually, because the median is what we report for expectation, for inflation, for example. But I agree that if you're interested in value at risk or something like that, you need to do something more sophisticated. Serena, you had a question?
Yeah, so I understand the parametric distributions might be limited, but how about mixture of distributions, like mixture of normals? What do you gain for certain moments that you can target your approach that simple mixtures?
I mean, that's a good question. We haven't compared with mixtures of distributions, but the caveat that it has is the same as any parametric distribution. So even if you fit the data perfectly, the issue that we cannot rule out expectations coming from densities that fit the data equally well here. So even if by using mixtures, we end up matching all the bins exactly, unlike the generalized beta examples that I showed you, we are not still sure that the mean implied by the distribution is the only mean. There are other values of the mean or other values of expectations of G functions that are consistent with the data, equally consistent, but we cannot rule them out. And here we're choosing one by making a parametric form, a functional form assumption. So that's what we're trying to avoid here. These bounds will not have that caveat. So in my last, well, I have 15 minutes or 12, I think. I want to tell you briefly how we implement this. And then I will show you what we get when we go into the survey of consumer expectations, DSE. Okay, so the smoothness part is as follows. We're going to use the fourth derivative. We have tried with other derivatives, so let's focus on the fourth. And then we need to choose phi. Phi will be, I will show you results coming from two choices of phi. One is just the minimum phi, which is the tightest possible bounds that we can get in this problem. This will be our reference, but not necessarily, again, we don't have any extra information to discipline the choice of phi, so here this is just to have a reference point. And then our preferred choice, which is a pilot density approach. So what we do here is we feed a bunch of densities to the data, we penalize the ones that don't fit the data very well, we focus only on the ones that fit the data quite well. And then we use the maximum absolute force derivative from that density, and we look at all the possible means that consistent with that derivative. So that is the phi pilot that you see there. So we will look at these two. And naturally, the phi pilot is greater than phi minimum by definition, sometimes much greater. It depends on the underlying densities. The candidate densities here will be the generalized beta and the skew normal, which are the popular choices in practice. So we do something a bit more sophisticated, but that's the broad idea of this phi pilot approach. For the beans, we use exponential tails. I have a button to Frank before lunch. I can show you what happens when I click there. But for now, these are just exponentially declining dominating functions for what happens on the tails. And then we need to calibrate the rates of the left and the right tails. And we do that by ensuring that there is not a lot of probability after a very, very extreme value. Essentially, the extreme value is like inflation in the US cannot be like inflation in Argentina, something like that. Because this is 1 year ahead inflation. That's the example I'm going to use too. And then we use like 1,000 grid points. So the data I'm going to show you is, again, 1 year ahead inflation expectations, or the survey of consumer expectation. You have already seen the box. That's what people were filling in, and the pies are coming from there. We are going to look at a sample that's selected as follows. We will ask people to not put all probability in one bin, or to not put zero probability in something in between. So if they put non-zero probability and then something in between is zero, we get rid of that. This is not for our method. Our method will still work. It will give you something here. No, there's always a solution to this problem. It is for the parametric estimation approach. Also, the generalized beta doesn't work if you don't have these restrictions. With these restrictions, we end up with 141,000 responses that so we compute these many, many times, as you can imagine. And a large fraction of them, like 45%, include extreme beans. No? So like 55% don't, and then we have these extreme beans in many of the responses. So what are we trying to do? What I will try to show you now is trying to answer three questions. One is, how much do we gain relative to just using the hands-off approach that doesn't use any information about what happens within each bin? That's question number one. Question number two is, how consistent are the implications of parametric densities compared to our bounds? And finally, how the bounds change with phi, in particular comparing the phi minimum with the phi pilots. That's the goal here. And I have a bunch of pictures to show you. So let's start with two individual responses. So let's look at this at the individual level. This is a response where the individual didn't put any mass on the tail beans. So here there's nothing unbounded. We don't use any additional restriction. We just use smoothness as our restriction here. The gray bars are the responses. The orange bars are the response, the beam probabilities implied by the best fit in generalized beta distribution. And then you have the intervals there. So the hands-off approach gives us an interval that's about 2.4 percentage points wide. Now this is inflation again. 2% is the inflation target. This is a very, very uncertain calculation. Our bounds narrow down to an interval that goes from 2.2 to 2.6. So that's a substantial increase in precision. Again, only using this is the pilot approach, by the way. So even the more conservative approach gives you that. The generalized beta mean is 2.16. It's outside the interval. So here it doesn't look as if it fit the data that badly, but it fits it badly enough that it ends up being outside the interval. Another example, same pattern. Now the generalized beta is above. It doesn't need to be below. I mean, there is no prediction of in which direction generalized beta will be. Same patterns. EMW hands-off bounds are very wide. Our bounds narrow this substantially, and then the generalized beta mean is outside the interval. And this happens very frequently. Also, but here I showed you just 2 out of 141,000 responses. Let's try to see what happens when we aggregate the responses. So this is what you're seeing here. On the left, what we do is a scatter plot where we plot the length of the hands-off bounds compared to the length of the pilot approach. Also, by construction, these are all above the 45-degree line, which is the line that you see there. All the red dots are like the scatters for this. you see substantial increases in precision. The median gain is something like 1.7 percentage points, which is more or less in the order of what I showed you before. So that was not a crazy increase. For 25% of the respondents, the increase is about 4%, because sometimes you end up with very wide bands just because a lot of probability goes to the extremes. And then you have the distribution of the gains, or the ratios of the lengths. You see there is substantial mass close to 0.1, 0.2. So these are intervals that are like 10% or 20% the original length from the EMW approach. When we use the minimum phi, we get, of course, a lot more. The new figure now is the same relative to EMW, but minimum phi, I should have done like pilot versus minimum phi, but yeah, this is what we have here. Two things to mention. One is minimum phi certainly gives tighter bounds. That's not surprising. That's just a theorem. But even after we use the minimum phi, we still get substantial uncertainty. Also, for some of these people, we end up with lengths that are like 2.6 percentage points. So there are people for which their responses are such that, yes.
Sorry, I don't understand. Because I thought the minimum phi would just give you a single density.
No.
Why not?
It doesn't. Because this set that we have here, I mean, this set has, no, it doesn't collapse to a singleton. No, it's just, you end up with positive and negative, with minimum and maximums that are not necessarily the same. It just gives you the tightest possible set, but it doesn't necessarily become a singleton. It's not just a single density. That's consistent with the data. Because I mean, think about what we're trying to do here is we have these bins. These are 10 numbers that we're trying to match with the density. And then you can draw different densities, each of which has this upper bound on the derivatives that we have here. This one. But they are all different. And when you integrate them, you end up with different means.
Is this because you discretize things?
It's not because we discretize necessarily, because even in the continuous problem, you end up with maximums and minimums that don't agree. It's just because the information we get from the agent is finite. We don't ask the agent to give us the probability for every single event, and then we can fill in the gaps in many different ways. That's why. Even in the continuous case, it's just because we have these 10 numbers to match. We can match those 10 numbers in more than one way. That's why.
Can I ask a question related to that?
Yes.
Which is drawing on the fact that you're analysing the results of this survey, but you guys are at the New York Fed. You also designed the survey.
Yes, I don't.
You don't personally, but
yes.
you talk to people who are affected. So is there a moment or a question you could add to the survey that would maximally help you in this problem?
Yeah, that's a very interesting question. I don't personally know the answer, but I think this could help design. What you're asking is there like a better design of the bins or something like that?
Not necessarily the bins, but you could also ask them for their expectation or the median directly. That's another question.
Yeah, no, that's a good point. There are a lot of difficulties in asking things that are more complicated than the bins, and I want to let Gisem also chime in. But yes, Gisem, go.
I'll just say one thing. You do ask the point forecast as well, but it's not really clear what the point forecast captures. For some people it's the mode, for some people it's the median, and that's why like the density of recitation is like favored over the point forecast for many reasons. So it's a little bit hard to ask something that would be like the same for everyone, because like we can't really go into their minds and like kind of prompt them.
Let me try to conclude. So one last figure, and then I will just skip the regression part as I planned. Here we have the mean implied by the generalized beta compared to the midpoint of our intervals. And as you see, they don't always align too well. Also, this phenomena that I showed you in some individual responses, that the mean is sometimes outside the interval, is quite systematic. We see it quite often. And actually, you see the fractions. For the pilot density, it's like 30% of the time. Sometimes it's inside the interval, but it doesn't align with the midpoint, which is what you see in the figure. If we use the minimum phi, then this raises to 88% of the time. So it's very frequently inconsistent with the data. And to the point that it just is ruled out by our bounds. Okay, so last 2 minutes. I mean, I don't have time to cover the regression part. We just the idea here is very at a very high level is we will use the bounds that come from our previous calculations, either as y or x in a panel regression. This is a problem that's connected to some of the problems that have been studied in the literature, so we adapt a lot of those techniques to this setup. One interesting application is Euler equations. So if you have an Euler equation, you can do a Taylor expansion, and then regressing the expectation of consumption growth on square consumption growth, the expectation of square consumption growth divided by 2. That identifies the relative prudence parameter. So this is a panel regression, and we have the data to do it. And actually, this is one of the calculations that we do in the paper. But let me conclude. So I want to conclude with 3 ideas. One is that beans or intervals, these survey designs, is informative about a lot of things that relate to the subjective probability distribution that people have in mind when they are doing predictions, something like that. There is information there, but that information is not absolute. So we don't point to identify a lot of objects of interest. So in this paper, what we do is we propose a way of still representing the data in a very honest way, but introducing structure to have more precise intervals. And then we show how to use this subsequently in regression analysis and other problems. There are a bunch of other questions that we don't cover in this paper that we're working on, one of which is what happens when we have joint expectations for different objects. So we can think about multivariate objects like covariances or correlations or regression coefficients or something like that, or joint CDFs. These are things that one can incorporate into our setup as well. One can extend our tools to deal with those as well, and that's what we're trying to do in the future.
Do any surveys actually ask about joint stuff, or are you turning univariate densities into joint by assuming a copula?
No, but there is it's part of the future work to incorporate those into the surveys. We ran a special module actually in the SE trying to do this for income. And yes, this is something that's, again, it's an area in which there will be a lot of work in the future, I predict.
Great. Thanks very much. Okay, to stay on time, if you have any questions, maybe over lunch, but to stay on time, we'll have the next paper presented here on stability of inflation expectations.
Okay, so I want to thank Jonathan and Alan very much for putting this paper on the program. This is joint work with Stefano Giglio, who is at Yale, and Puya Molody, who's right here. I'm at the Fed, and so the usual disclaimer applies. So this paper, we're thinking about anchoring of inflation expectations. This is a core kind of stated, at least like intermediate objective of monetary policy, is that if we can keep inflation expectations anchored, that might help keep inflation itself anchored. And so what that is typically taken to mean is that expectations are not too sensitive to news, right? So you could think about either expectations are not moving too much, or that when we get high inflation or high other signals about inflation, that people's expectations are not too sensitive to that. And so we're going to try to think about that, where we want to try to measure that in the data. The basic setup that we're going to start from is that if you have an agent that has an arbitrary prior, and they have signals that they think are normally distributed, then the sensitivity of their expectations to the news that they see is going to be equal to their prior variance multiplied by the precision of their signal. And so basically the Kalman gain formula that you get in a linear Gaussian model actually holds locally under much weaker conditions. And so if that's true, what that lets you do is, if you can measure uncertainty in real time, so from density forecasts, that's going to tell you then how sensitive people are to any additional signals that they get, kind of holding that precision fixed. And so what we want to do in this paper is try to test that idea and measure how strong it is in the data. The core difficulty here, what's going to make this hard, is that uncertainty is endogenous both to precision, so people that have imprecise signals are going to tend to have high uncertainty. That's going to cause us problems. And that uncertainty is also going to be endogenous to the signals themselves. So again, if I have normally distributed signals, the basic statement is that the derivative of your expectation with respect to your signal is equal to your uncertainty, it's actually your posterior uncertainty, multiplied by the precision of that signal. And so what we want to do is kind of ask, to what extent does that help us measure how well anchored expectations are, right? That if we can measure uncertainty for individuals, is that going to tell us something about the extent to which their expectations respond to the signals that they're seeing. So the data that we're going to look at is going to be from the survey of consumer expectations. We will look at how people's expectations change. So we're going to use the panel structure of that survey, how they change in response to signals, in response to realized inflation, really, and how that relates to uncertainty in the cross-section. The unconditional correlation, if you just run an OLS regression and you compare responsiveness to realized inflation or just the volatility of expectations, you compare that to a given person's uncertainty, you get a correlation that's weak or even potentially negative. And where we think that's coming from is just that there's an endogeneity here, which again is that the low precision agents also have high uncertainty. And so then it's not clear, if you look at the right-hand side of that equation, it's not clear whether that moves positively or negatively with uncertainty itself. And so what you need then, if you want to try to evaluate the extent to which uncertainty itself is moving that sensitivity around, you're going to need an instrument for uncertainty that's orthogonal to precision. And so what we're going to use in the paper is people's tenure in the survey. The idea is that when people are in the survey, so when they enter the survey, they're getting asked a bunch of questions about inflation, about other aspects of the economy. When they're in the survey, that causes them now to pay more attention to all of these things. That's going to then progressively, it's going to cause their uncertainty to progressively drift down, which is what we see in the data. Drift has been noted previously, so we didn't come up with that. That's in Kim and Binder. And you can use that then as a source of variation in uncertainty across people. So you basically ask, you have these people who have been in the survey for longer, their uncertainty is lower. Are those people then less sensitive to realized inflation, and are their expectations just more stable overall? So the identification then is not treated versus untreated, it's essentially in the duration of the treatment. So the longer that you've been in the survey, the longer you've had this treatment, and that's what's affecting your uncertainty, and what we're going to use as our source of variation. So what we're going to find in the data, number one, at the micro level, we get a strong relationship between uncertainty and the strength of anchoring, according to a few different measures. We run similar regressions at the macro level, where we actually don't need any kind of instrument, or at least we don't use any kind of instrument, and we actually get a similar time series relationship. So if you just look at the relationship between the sensitivity of expectations in the aggregate SCE, how that moves with aggregate uncertainty in that survey, that's consistent with what you get in the cross-section looking across people, where the variation's coming from tenure. The last thing we'll do is try to think about, so basically the point here is that you can use uncertainty in real time as a measure of how well anchored expectations are. And what we'll then do is try to understand what drives uncertainty. And so the same sort of analysis that gave us that derivative for your expectations also gives you a derivative for your uncertainty. And essentially what you get is that high inflation is going to raise uncertainty when people have positively skewed beliefs. And so we'll look at that in the data. We see positive skewness for these beliefs, and so that's going to be consistent with the increase in uncertainty that we got as inflation rose in 2021 and 2022. So that's what we're going to do. We're building on a big literature. There's tons and tons of work on this, both on this survey. We've seen 2 other papers on this survey so far today, but also on, again, how do you elicit moments? How do people update in surveys and experiments? And we're trying to add one little piece to that. Yes, please.
It's a really dumb question, but if you just wanted to look at this anchoring issue, how about just looking at surveys where you have short-term inflation forecast and then you have long-term forecast, and then you look at the, for agents, is there some correlation in the deltas, the revisions in short-term versus the long-term?
Yeah, absolutely. So that exists in the literature. That is one way to try to get at this. Essentially, the way to think about what we're after here is that on some level, you could potentially imagine doing that in real time, right? If you're willing to put enough structure, like if you really think it's an AR1, then a single observation is enough for this. But outside that, without that assumption, you're going to have trouble. Like if it's an AR2, that doesn't work anymore, right? You need a kind of a longer time series. What we're after, the basic claim that we want to make is that if you just measure the second moment, that's enough, right? And that's what we're going to take that approach. Absolutely not the only approach. There's lots of other ways to try to get at this. So the basic structure that we're going to be thinking about here is that we have a latent object we're going to call pi star. Think of pi star as, it could be a latent trend for inflation, it could be future realized inflation. We're going to let that follow an arbitrary process. So I don't want to force that to be a linear Gaussian process. I don't want to force it to be an AR1 or AR2 or any of these things. In particular, for inflation, I want to allow it to be non-normal. I want to allow it to be positively skewed and have volatility that's moving around over time, because we see all these things pretty strongly in the data. So there's some pi star. That's the thing that people are getting information about. And the structure of their information is going to be that they see a signal yt. Yt is going to be normally distributed conditional on pi star. So think about it as just pi star plus a normal residual, and that the residual has variance sigma squared t. So we can have non-normal prior, non-normal dynamics in the background. We just need normally distributed signals. And those signals have a precision sigma to the -2. So this, right now, there are no person subscripts. They're just time subscripts. So think about this as a model for one person. And like every person is going to have different priors, different models, different sigma squareds. Yeah?
So are you assuming that YT are conditionally independent over time, conditional on pi t star?
Yes. Every period I see pi t star plus epsilon. That's what I get.
So the way to think about this is that it's more like measurement error or like very short-term shocks rather than persistent shocks.
Yes, these are that I'm getting. I have a bunch of signals. All those signals I can aggregate into some thing. That thing is y. That's capturing all of my information. That thing is telling me about the truth plus some noise on top of it.
That thing doesn't depend on the past. That's
So it could depend on the pass and you extract it, right? So this is a reduced form setup, right? You could imagine that the actual thing that you see is y, and y could be an AR1, right? And it depends on past y and past things I've seen, and I can extract those, and I can come up with a component that is telling me about what's going on right now. And that's the thing that I'm calling y. Y is the novel information that I have that I did not previously have.
But I thought what you meant is YT minus pi t star are independent across time, rather than having some AR structure.
So I want to distinguish between the thing that is on the slide and the thing that people actually see. So the thing that people actually see in the world is some rich thing that probably has lots of dynamics of its own, and it like depends on the past and is some big complicated process. What matters when you're doing forecasting is just the part of that information that is new, that is not spanned by the previous observations, right? So I could imagine there's a y hat. Y hat could have some complicated dynamics, and then we're going to think of y as the innovation in that y hat process, and that's the novel information, and that innovation is what I want to be pi star plus noise. Think about this as just kind of a totally boring like filtering setup, right? We're just trying to set up a filtering model. There are countless ways that you could make it more complicated to make it more realistic. And so what is critical for us is thinking about how do expectations respond to the novel part of the information that you get. So we're going to define, when I say expectations, I mean the conditional mean of your beliefs. So I'm going to call that M. That's the mean of your conditional distribution for pi star given the history of signals that you've seen up until date t. I'm going to define your uncertainty to be your conditional variance. There's a reason that I wanted variance and not standard deviation. But so it's going to be everywhere that I say u, I mean the conditional variance of pi star. It's the posterior variance. We're going to assume that everybody updates via base formula. We are not assuming that they have rational expectations, right? So I'm assuming they use base formula, but they could be using all the wrong inputs into that thing. Their model of pi star might be wrong. Their model of y might be wrong. They might be paying attention to the wrong things. All of these things could be wrong. I'm going to show you really a derivative of a formula as opposed to anything about people being completely rational. If they're using base formula, you can essentially just take a derivative of it, and what you get, you take a derivative of the conditional mean formula. And what you get is that the change in your mean is going to be to first order equal to your current uncertainty, it's actually your posterior uncertainty, multiplied by the signal precision, multiplied by the surprise in the signal. So y minus what I thought I was going to see given the information that I saw up to t minus 1, right? That's what that guy is. Plus whatever I think the drift is in the underlying process. So what is this? this is simply the Kalman filtering formula. And the point is that that holds to first order regardless of what my prior is and regardless of what the process is, the underlying process is for the pi star. So the local sensitivity of beliefs to the signals is just a derivative, and it's equal to my current uncertainty multiplied by the precision of the signal. And so the usual like fully Gaussian update is going to hold locally for arbitrary priors. This is somewhat well known, but it's useful, so we're going to use that. Slightly less well known, but still useful and still not hard to derive, is this result about updating uncertainty. So the change in my uncertainty has three terms. Two of them you would get in the normal linear Gaussian case. So one is the information flow. So the more information I'm getting, the lower my uncertainty is. The information is going to be, so if I have high uncertainty, the uncertainty is falling fast. And if the precision of the signals is high, the uncertainty is falling fast. There's variance coming from updates to the latent state. And then there's also a third term, which is that the change in my uncertainty in a given period depends on my signal precision multiplied now by the third moment of my beliefs, multiplied by the surprise in the signal. And so there are two things here that are going to matter for us. One is uncertainty is endogenous to signal precision. So people who are paying more attention, who are getting more information, they're going to have relatively lower uncertainty, right? That the sigma squared and the u are going to be correlated with each other in the cross-section. And number two, uncertainty is driven by the same signals as expectations, right? The same thing that moved your mean is also going to move your uncertainty if you have a non-zero third moment, right? So if you had normal priors, then that term disappears. If you have non-normal priors, so say you have positive skewness in your beliefs, so you think that inflation has a long right tail. If I give you a signal telling you that inflation is higher than you thought, that's going to increase your variance because now you're in the wider part of the distribution.
How important is the assumption that the signal is Gaussian distributed?
So to get these formulas, you need that. You can get versions of them without that, but you're not going to get, so what you're certainly not going to get is this clean third moment showing up. And you're not going to get everything to be, like the specific structure here is not going to go through in the same way. So you get like, there's a generic result that entropy has to be declining, but beyond, like with any signal, if you're a Bayesian or if you update using Bayes formula, the posterior entropy has to be lower because you've gained some information. It's hard to say anything beyond that when you allow for kind of arbitrary signals.
What do you have here in mind, and what are the signals that you're thinking about in the application?
So I think there's a few ways to think about this. So one is that, so one you can think of as like as a martingale central limit theorem kind of argument, that if people have like a whole ton of signals that have arbitrary distributions but are minimally informative, then those are going to aggregate up to a normally distributed thing. Another possibility is that they really do observe signals that are normally distributed, and they could have many of those, and you can always aggregate those into a sufficient statistic. Another possibility is that you could imagine a person, I mean, we use things like this precisely because they're tractable, right? And so you could imagine following this behavior, even if this doesn't need, again, the claim here is not that this is the DGP. That's not what we need. What I need is that people are acting like this is the DGP. And so a lot of times, like if you think about the literature on forecasting, there's a huge amount of normality that floats around, like not always, but like a lot of times when we start thinking about distributions, we have that there as a baseline. And so I think it's not a completely ridiculous starting point. But like absolutely, you can certainly imagine signals that are not normal. You could also imagine that people are getting signals not about pi star, but about like pi star squared, or about is pi star above 0. Like there are lots of ways to move this. And so we can relax the structure that people typically use in certain ways, in the sense that pi star can be anything, which is nice, but we're still stuck with normality. The only other thing I'll say is that if you have a specific alternative distribution you want, then you often can get versions of this formula. So like Poisson arrivals have like a really nice clean version of this. Like essentially any exponential family is going to give you something like this, but it won't be the central moments anymore.
Yeah, I was going to suggest that mixtures of normals seems such an obvious thing to do here, because like I don't know if you're going to look at COVID, right? But it would be a reasonable assumption that was drawn from another normal distribution, right? So you still get your exponential tails, and so would that formula then reoccur in some slightly, more complicated?
So there is work on, the mixture models are great for filtering in practice. The problem is that things, if both your prior and your signal are mixtures of normals, then your posterior is the product, and so everything explodes, which you can handle. Like, there are ways to deal with this, but we're not going to cleanly get that formula. And so to be clear, it's not, so again, the prior could be a mixture, right? The prior could be bimodal. It could be that I think in the background there's some weird thing happening with inflation and I don't know which direction it's going to go, right? I think it's going to be far in one of two directions and it's not going to be in the middle. That's okay. It's just that you're conditional on that. The information that I'm seeing about inflation has to be centered on the truth and has to be normal. That's the thing that that's the restriction that we need. As an aside, that recursion actually keeps going. So if you, actually I'm not going to talk about this. I don't have time for this. It's in the paper. I'll refer to you to our other paper, and I'll leave it at that. It's a nice theorem, but I'm not going to talk about it. So we're going to use data from the Survey of Consumer Expectations, which we've already seen a couple times today. So this is, again, a monthly panel of consumers, which this panel aspect is what's important for us. We're, again, going to use these bins that are 0 to 2, 2 to 4, 4 to 8, 8 to 12, greater than 12, and then the same thing on the left-hand side. And we're going to use those for our densities. We totally agree on this issue of that it's hard to get moments from these densities. We are going to do the beta thing explicitly because we wanted to not do anything. You look at it and you're like, oh, I bet I could do better than that. But we don't. First of all, we probably couldn't. Second of all, not in this paper. So we're going to take the standard beta thing, and we have both the point forecasts, and you can use the bins to get individual level expectations and to get individual level variances. So now I have my I subscripts for the individual people. We will look at both the 1 and 3 year expectations, and our sample is going to be 2013 to 2025. For some of the analysis, we're going to use the inflation surprise as at least one piece of information that people get. So person I's surprise in inflation is realized inflation, which you could measure different ways, minus their expectation in the previous month. What we're plotting here is uncertainty as inflation moved. So again, 2013 out to 2025. Green is annualized monthly inflation. And then red and blue show you what the uncertainty looked like. It's on the right-hand axis. So it pops up when inflation went up. It comes back down, but it actually settles at a level that's about twice as high as it was prior to COVID.
So I'm confused about the horizons here, because this is a 1-year inflation forecast, so you don't get to see that the next month.
Right, so we're going to take that, so we're going to use that 1-year forecast as the thing that we're using to measure the surprise. So absolutely, if they think that they have some other trend in mind, it may be that we're mismeasuring the forecast.
Well, but the surprise is observed a year later.
We're going to treat this, we're going to use the surprise the next month. We're going to take if I want to know the surprise in February, I'm going to look at February's inflation minus January's 12-month forecast of inflation.
Oh, wow, okay.
And so but to be clear, that's not all of the results, precisely because that might make you uncomfortable. We don't necessarily have to look at that. And so let me look at that. And let me talk about that. So there are two things we could do. So one is to not do that. So forget I even said it. If it bothers you, let's not talk about that. Let's talk purely about this. I can just if we take all the equations that we have so far, the expected squared change in a person's expectations should depend on their current uncertainty multiplied by the precision of the signals. Right? And so there we're just measuring anchoring based on how volatile the expectations are and saying, look, a person who has high uncertainty should have expectations that are moving around more. And that's not taking any sort of stand on what it is that they look at. You can imagine that kind of roughly what you might like to be estimating here is average precision. You can also imagine that that might not necessarily work, that heterogeneous slopes kind of cause trouble, and so we'll talk about that. The other thing that you could do is say, I'm going to measure a response to realized inflation. So if you write down a trend plus noise model and you're willing to take a stance on exactly what that trend looks like and what the forecast is, then what you can get is that the change in the expectation is going to be your signal precision multiplied by this piece in brackets, which we're going to claim is observable, or at least, roughly observable, which is your uncertainty multiplied by the surprise in inflation. There's also obviously an epsilon. People observe lots of stuff other than just that inflation. Like, we certainly wouldn't want to make that claim. And so that's all going to be built in, and you do need to think a little bit about what that guy looks like, especially because we don't actually observe signal precision. And so the cross-sectional heterogeneity in people's precision, which you can think of as their attention, that's going to show up in the error term. It's potentially correlated with uncertainty, which will create problems. And so that's why we're going to need an instrument. So, yes?
So for this survey, it's the expectation month over month inflation or year over year?
So we have two different numbers that we'll look at. There's the forecast of inflation over the next 12 months, and there's the forecast of inflation in months t plus 25 through t plus 36.
Okay, so another thing here is that, yeah, I guess here, if you have the model, then in principle you can run the future until 12 months later, right? So you can, instead of looking at something like expectation of t minus 1 of that thing, you can look at expectation of t minus 12 of that thing. So that will match closer to what's the forecast is.
So we don't have that model. We haven't written down a model of the dynamics for pi star.
So is that not tractable, or is that like?
Well, that requires, then you have to take a stand on what the model is. So our goal here is to not take a stand on what the model is. So the idea is that, so again, the idea here is that this expression holds regardless of the dynamics for inflation expectations, right? And in particular, that derivative is going to hold regardless of what you think is going on with pi star in the background and with inflation in the background. And so the point here is to be able to try to get a measure of how sensitive your current expectation is to the signals that you're seeing without having to know anything about the model that you're using. And the point is that regardless of the model, if the signals are normally distributed, which again they might not be, but if they are, the derivative of your expectation with respect to the signal is going to be your current uncertainty, that is a sufficient statistic and I can forget about the rest of the model. And so then I don't have to try to forecast forward. You could do that. You could write down some parametric specification for what you think people do and then push that forward and get a forecast.
Instead of the surveys for the uncertainty piece, would it work to use volatility of market-based inflation expectations, something like volatility of inflation swaps?
So we're looking at that. So you could, there's always the difference between realized volatility and implied volatility. You might worry about that, and they're actually right now they're bickering over the contract so that we can have some of that data. So the first thing that we do is an OLS regression. So if we regress squared changes in expectations on squared uncertainty, you get a coefficient that I'm going to argue is small. So this you can think of as measuring the signal precision. So 1 divided by the square root of that would be the implied standard deviation of the noise in the signals. 1 over the square root of that is 24%. So these are all annualized. So it would be as though what I observe every day is trend inflation plus noise that has a standard, every month. Trend inflation plus noise with a standard deviation of 24 percentage points, which feels large. So I think this number is too small. I'm going to show you numbers that are bigger. I can also regress changes in expected inflation on the realized inflation surprise and the realized inflation surprise interacted with uncertainty. The people with high uncertainty are actually less sensitive to surprises in inflation. So this goes the wrong direction. Again, it kind of makes sense that the people that aren't paying any attention, that just don't care about inflation or don't think about it, they have really wide bands that they report in the density forecasts, and so then they're just not that sensitive to surprises in inflation. And so that's what we want to try to get around. And the way we're going to try to get around that is with an instrument. The instrument is going to be tenure in the survey itself. So the basic idea is that prior to the survey, so this is the period we don't see, prior to the survey, people have low signal precision, or it is what it is, and they have uncertainty, it is what it is, we just normalize it to 1. And then when they enter the survey, people are, I guess they're doing this on the internet, they're like going on this website, and the website's asking them a bunch of questions about all sorts of things about the economy, and inflation in particular. And that effectively we're going to think of as a higher information flow for these people while they're in the survey. So it could be that now when they see inflation in the news, it's more salient. It could be the survey itself contains information, right? The magnitude of these bins kind of tells you that plus 12 to minus 12 is the order of magnitude that we're thinking about. So maybe you get fewer people saying 1,000% for inflation. And so as their signal precision is higher, you're going to have uncertainty drifting down with the duration of their time in the sample. So this is the number of months since they entered the sample. So we're going to get relevance then from attention going up, causing uncertainty to drift down. And so again, the identification is not treated versus untreated, it's from the length of the treatment. And then for exogeneity, what we need is that within a given person, their signal precision or their attention is uncorrelated with tenure. So where we would potentially have trouble is if attention is falling with tenure, that's going to bias up the estimates. In the paper, we have a way to try to estimate that, but it's using some of the structure from the model, but it's tricky. We don't see any evidence for this moving, but that's the core assumption that we need. We want attention. We want people to continue paying attention while they're in the survey. This is an instrument. It turns out two-stage least squares is not well suited to this setting for a couple of reasons, and so we're going to use a control function approach, but I'm not going to, we don't need to get into that today necessarily. So these essentially are the results. The first stage is the top graph. So what I'm plotting here is across months of tenure, what is the average uncertainty across the respondents. So we get a variance of 18 percentage points on average at month 2, and that declines to a little bit more than 10 percentage points when you get to month 12. So people are reporting progressively narrower distributions the longer they're in the survey. Going down to belief volatility, if we look at the volatility of changes, so there's the mean squared change in expectations, that is largest for people with low tenure and smallest for people with high tenure. The magnitude of those changes declines by about half over those 12 months, which is consistent with a decline of about half over the 12 months in the amount of uncertainty that people have. If we look at the effect of news on expectations, so just within a given tenure bin, regress the change in expectations on the inflation surprise, that coefficient is largest at low tenure, and it declines again by about half when you go up to month 12. So the people in month 12 have expectations that are more stable overall and also are responding less strongly to inflation realizations.
Are you surprised that they are so similar for 1 year and 3 year uncertainty? Because if you have a highly persistent process, it will reflect the degree of persistency, of course, in the underlying GDP, which I know you're not taking a stand on for school, but I would have expected maybe a slightly larger difference.
So that's fair. I think you have probably two things going on. You have short run stuff that's going to be mean reverting, and then you have long run stuff where you have a random walk kind of component potentially living in the background, and it may be that those two things are canceling each other out to some extent. One thing you can note is these numbers are big. So this is the full sample. So we filtered out a lot of the really crazy people that have variances above like 200, but there's still some kind of crazies, and these numbers are still higher than you might expect. And so that's part of what you're seeing is just these are big averages. And when you compress it down to people with a college education who answer one of the math questions right and have income above $50,000, you get numbers that are a lot more reasonable. And things start to look, when you start to poke on rationality, it works better. When you make sure they can divide by 2 properly, then it all adds up a little better. But so that's the basic variation that we're working from. So this is the second stage then. If we actually use the instrumental variables estimator, what we get is the second stage estimate for the average signal precision. If we use, so we actually do get slightly different answers depending on whether it's 1 or 3 year inflation. You can use either the point forecast or the mean from the density forecast. What this is saying is that across these numbers, the implied standard deviation of the errors on the signal, right? So this is a measure of the average precision. The standard deviation of those errors is somewhere between 2 and 3.5%. And so that's starting to get to something that I think looks a lot more plausible as an amount of attention that people are paying on a monthly basis to what inflation actually is. So this is from the expectation volatility. Again, remember that was 0.0017 in OLS, and so we're larger by a factor of 100 here. When we do it using regressing the change in expectations on the inflation surprise, you get a smaller number. What that's saying essentially is that people are getting most of their information really from things other than realized inflation in this month. So that could be that we've just misspecified somewhat what their expectations were. So our measure of the surprise is not the surprise. That would push this down. But the other thing is that there are other policy announcements that are driving things. They might think that fiscal policy is driving things. Additionally, this, this is, we're using like CPI and PCE inflation, which are certainly not the only things that you could be looking at. You could be looking at inflation in lots of different sectors. You could be looking at core versus headline. And so we're getting numbers of say 0.01 to 0.02 here. And so we're gonna see that again in a moment. Yeah.
I'm wondering about the interpretation of this measure, because sigma square is not observed, right? It's more like a residual, like TFP type thing. So then this could be not only about the precision of the signal, but could also be about, say, inattention of the consumer, or even misunderstanding of what kind of inflation this survey is about.
For sure. So we want to, yeah, so absolutely. So definitely some of the text has used both of those terms. And the paper is much more clear about this. What this is about the information that's getting into people's heads, right? And so that's going to depend on their attention. It's going to depend on what they're looking at, right? That like what the model, that signal that people are seeing, that is person specific. Right? And so this is not a statement about what is the true information content of inflation. It's a statement about how much of that information, like you said, gets into people's heads, which is going to have to do with their attention, it's going to have to do with their sophistication, and with all the other things that they're looking at. And so that's really my preferred interpretation of this, is that the cross-sectional variation that creates that endogeneity is that some people pay less attention. They have access to the same information that anybody else does. They don't pay much attention, and so they just don't know what their uncertainty is very high because they're not really looking at inflation data, which is on some level most people, right?
So if you think the same thing of professional forecasters, are you going to see that this number is much larger?
You would. So that's a potentially different. Certainly in the context of their response to inflation, that's a somewhat different question. The short answer is I don't know. So the reason we don't use the SPF is because it's quarterly. So 2 reasons. 1, it's quarterly. 2, you don't have this instrument. And so we have no source of variation in their uncertainty. So for example, you could have different forecasters who think that inflation has different information content. That will then change. Like even if they see all the same data, they are using different models, then all their moments are going to be moving differently. The last thing I want to look at is aggregate time series regressions. So the panel data, what's nice about it is that it lets us try to be careful about endogeneity and identification. At the aggregate level, we're not going to have an instrument, but on some level for policymakers, this is often what you care about, which is that really we just want to forecast what our aggregate expectations doing. And so that's not so much an identification problem as just a pure forecasting problem. And so when we think about these time series regressions, these are not going to be about testing-based formula, but they're informed by that because the model says you might want to look at uncertainty. It suggests that that's a natural thing to be trying to forecast with. And so essentially what we want to ask is, does uncertainty predict the volatility of expectations? So like now aggregate expectations. So does aggregate uncertainty predict the volatility of aggregate expectations, or the sensitivity of aggregate expectations to realized inflation in the time series? And so that's what these regressions are doing. I have results for 1 year and 3 year expectations. This is regressing your expectation on the inflation surprise. This is just looking at squared changes in expectations. So if I look at squared changes in expectations and I regress that on lagged squared average uncertainty across people, I get a coefficient of 0.2 to 0.4, 0.002 to 0.004. So that's a good deal lower than what we saw in the micro evidence. But it's closer to being consistent with this guy, which is the sensitivity of aggregate expectations to realized inflation. And so that number, that 0.005 to 0.009, that looks a lot like what we had here. So they're not statistically distinguishable from these numbers. So what we're getting is that over time, in periods when aggregate uncertainty is higher, aggregate expectations are more sensitive to uncertainty. The coefficient on the inflation surprise itself is actually not distinguishable from 0, which is what the model says, that a person with 0 uncertainty should have 0 responsiveness to inflation. And so that's what we're seeing here. And again, that coefficient is consistent with the micro estimate. So what this implies then is that variation over time in uncertainty that we observe in the data is telling us something about the sensitivity of expectations to inflation surprises. So that's what we're plotting here on the left. The green is the sensitivity of 1 year expectations. Orange is the sensitivity of 3 year expectations, given what the model said. And so what this is telling us is that the actual realized sensitivity in the data rose by a factor of, say, like 4 to 5 between essentially 2020 and then the peak of inflation in early 2022. The 3 year expectations also moved, but by a smaller factor. That's using the cross-sectional mean of uncertainty. You get something similar with the cross-sectional median. And so the point here then is that uncertainty rose a ton as inflation went up, which is saying that sensitivity to further inflation surprises went very far up, right? That if we had had more inflation surprises, that we should have expected expectations to be much more sensitive to every progressive increase in inflation, but also that the fitted sensitivity is right now a good deal higher, like twice as high as it was pre-COVID. So even though expectations look somewhat anchored right now, they're kind of close to where you might want them to be, they appear much more sensitive to realized inflation than they used to be. Now, you could ask why that is. So remember, if we go back to the equation for the dynamics for uncertainty, what we get, again, is that the responsiveness of uncertainty to the actual signal that people see depends on their third moment. So if people's prior for inflation has a longer right tail than left tail, right? So they think there's a long right tail of possible outcomes, then when I show them information that says that inflation is going to be higher, their variance should go up. And that's what we saw, is that as inflation went up, variances did go up, right? So that's this. So here, as inflation went up, the variance of the distributions that people report went up. And at the same time, if you look at their third central moment or the Kelly skewness, both of those were positive through the entire sample. So these are people that have beliefs. They have priors that are skewed to the right. So they think there's not a lot of chance of inflation going too far below where the center of their distribution is, but there is a long right tail. And so then when they saw inflation rising in 2021 and 2022, they're now in the wider part of the distribution. Their uncertainty goes up, and you're mechanically then going to get this increase in sensitivity and essentially de-anchoring. And so this is, you can think about this third central moment then as being kind of a second order measure of anchoring, that you can ask how well, so there's like sort of, we can do 3 orders here. There's our expectations where we want them to be. So that's not anchoring, right? Your boat could be in the harbor, but it's not anchored to anything. It's just in the right spot. The variance tells me how well anchored it is, right? So how sensitive is the boat going to be to anything that sloshes it around? And then the third moment is how robust is the anchor, right? That if something happens, will the anchor weaken? And when you have positive skewness in your beliefs and a positive third moment, the anchor's becoming less robust, and in fact, it was least robust when inflation hit its peak. That's when we had the highest third moment, and so when the variance would have been most sensitive to additional inflation. So the point of this paper is to basically start from this observation that under weak assumptions, the sensitivity of expectations to news, right, even without very much rationality, is going to be proportional to people's uncertainty multiplied by the precision of the signals that they get. And so density forecasts then give us a way of trying to measure expectational anchoring in real time. Empirically, in the cross-section, when we use tenure as an instrument, high uncertainty leads to a stronger response of expectations to news, and that looks broadly consistent with what we see in the time series. And then post-COVID, so like up through now, inflation has come back down in the neighborhood of post-2020 level, pre-2020 levels, so like the CPI data just a couple days ago was great, but inflation uncertainty hasn't. Right? And so what that suggests is that even though inflation has recovered, the anchor may now be persistently somewhat weaker than it was prior to that big increase in inflation. Right? Thanks very much.
Thank you.